4.24 light-years away. That's the distance to our nearest stellar neighbor. Close enough to reach in a human lifetime if we could travel at just 10% the speed of light. Far enough that the light you're seeing from it right now left that star when you were planning what to have for dinner 4 years ago. This is Proxima Centauri, and it's not just our closest neighbor, it's one of the most fascinating objects in our cosmic backyard. Stand outside tonight. Look toward the constellation Centaurus. You won't see it. Proxima Centauri is invisible to the naked eye, a red dwarf so dim that it took until 1915 for Robert Innes at the Union Observatory in South Africa to even notice it existed. While the brilliant Alpha Centauri A and B had been known since ancient times, this faint companion lurked in the darkness, overlooked. And yet this unremarkable star may hold the key to humanity's future among the stars. Red dwarfs like Proxima are the universe's ultimate survivors. While massive stars burn bright and die young in spectacular supernovas, red dwarfs sip their hydrogen fuel so slowly that they can burn for trillions of years. Not billions. Trillions. The universe is only 13.8 billion years old. Proxima Centauri will still be shining when the universe is 1,000 times older than it is now. Every red dwarf that has ever formed is still burning today. Not one has ever died of old age. Think about that. These are the first stars born at the dawn of time, and they'll be the last lights burning at the end of everything. Proxima is small. Really small. Just 12% the mass of our Sun. If you could stand on its surface, though you'd be instantly vaporized, you'd barely feel more gravity than you do on Earth. Pack it with mass, and you need about 8 Proxima Centauris to equal one Sunday. In terms of radius, it's only 14% the width of our star. It's barely larger than Jupiter, even though it contains about 80 times more mass. This is a star compressed into planetary dimensions, a nuclear furnace squeezed into a space not much bigger than a gas giant. The surface temperature tells the same story of restraint. Where our Sun blazes at 5,500 degrees Celsius, Proxima smolders at just 3,000. That might sound hot, but in stellar terms, it's positively cool. This low temperature gives it that characteristic red glow, though you need a telescope to see even that. Its luminosity is a mere 0.17% that of our Sun. If you replace the Sun with Proxima Centauri, Earth would be plunged into an eternal twilight, receiving barely enough light to see your hand in front of your face. But here's where it gets interesting. In 2016, astronomers made an announcement that changed everything. They'd found a planet. Not just any planet, a rocky world orbiting in Proxima's habitable zone. They called it Proxima Centauri b. And suddenly, the nearest star to our Sun wasn't just a curiosity for astronomers. It became the closest potentially habitable world we know of. Proxima b orbits its star every 11.2 days. That's right, its year is shorter than 2 weeks on Earth. This isn't because it's moving impossibly fast, though it is moving at roughly 55 kilometers per second. It's because it orbits incredibly close to its star, just 7.5 million kilometers away. That's less than 5% of Earth's distance from the Sun. You could fit 18 Proxima b orbits between Earth and our Sun, with room to spare. At that distance, you might think the planet would be fried. But remember, Proxima is cool and dim. At this distance, Proxima b receives about 65% of the light and heat that Earth gets from the Sun. Not identical, but remarkably similar. The planet itself is intriguing. With a minimum mass of 1.17 times Earth's mass, it's potentially rocky. Potentially terrestrial. Potentially, and this is the word that keeps astronomers awake at night, habitable. But potentially is doing a lot of work in that sentence, because the reality of Proxima b is far more complex than a simple habitable zone calculation suggests. First, there's the problem of tidal locking. Orbiting so close to its star, Proxima b is almost certainly tidally locked, meaning one side perpetually faces the star while the other faces eternal night. The same hemisphere always in daylight, baking under Proxima's red glow. The same hemisphere always in darkness, radiating heat into space. Earth experiences this phenomenon with the Moon. We only ever see one lunar face. But imagine living on a world like that. One side in permanent day, the other in permanent night, and only a narrow twilight band between them where temperatures might be moderate enough for liquid water. The temperature extremes would be staggering. Computer models suggest the day side might reach temperatures well above the boiling point of water, while the night side could plunge to nearly absolute zero. Unless the planet has a thick atmosphere. A substantial atmosphere could redistribute heat from the day side to the night side, potentially making much more of the planet habitable. Scientists have run simulations with atmospheres similar to Earth's, thicker atmospheres rich in carbon dioxide, even thin atmospheres like Mars. The results vary wildly. With the right atmospheric composition and pressure, Proxima b could maintain liquid water across significant portions of its surface. Without it, any water would either boil away on the day side or freeze solid on the night side. But atmosphere is just the beginning of Proxima b's problems. There's also the stellar wind. Our sun produces a solar wind, a stream of charged particles that flows out through the solar system. Earth's magnetic field deflects most of it, protecting our atmosphere and making auroras at the poles. Proxima's wind is estimated to be at least 10 times more intense than our sun's. Some estimates put it at 100 times stronger. Without a powerful magnetic field, that wind would strip away Proxima b's atmosphere over millions of years, leaving it as barren as Mars. Does Proxima b have a magnetic field? We don't know. Earth's magnetic field is generated by the churning of liquid iron in its core. For Proxima b to have a similar field, it would need a molten metallic core and sufficient rotation. The tidal locking complicates this. While a tidally locked planet can still generate a magnetic field, look at Jupiter's moon Ganymede. The slow rotation compared to Earth's 24-hour spin might weaken any protective magnetosphere. Then there are the flares. Oh, the flares. Proxima Centauri is what astronomers call a flare star. These are common among red dwarfs, prone to sudden, violent outbursts of energy. In March 2017, less than a year after the discovery of Proxima b, astronomers observed Proxima brighten by a factor of 10 over a period of 10 seconds. 10 seconds. The star's luminosity increased 1,000-fold, unleashing a burst of ultraviolet and X-ray radiation. For 10 seconds, anything on the surface of Proxima b would have been subjected to radiation levels far beyond what Earth experiences during the most intense solar flares. These flares happen regularly. Not every day, but frequently enough to be a serious concern. Some flares increase Proxima's brightness by factors of 10, 20, even 100 times its normal luminosity. Each time, the planet is bathed in high-energy radiation that could strip away atmospheric particles, damage any organic molecules, and make the surface a hostile environment for life as we know it. One study suggested that over the course of several billion years, stellar flares could have stripped away an Earth-mass amount of atmosphere from Proxima b. An entire atmosphere, lost to space, torn away by the angry eruptions of its parent star. Yet life is tenacious. On Earth, organisms thrive in places we once thought impossible. Bacteria live in boiling hot springs, in Antarctic ice, in the crushing depths of the ocean, even miles underground. Radiation-resistant microbes can withstand doses of radiation that would kill a human thousands of times over. If Proxima b has liquid water, even intermittently, could life have found a way? Could organisms shelter underground, emerging only during calm periods between flares? Could an ocean, if it exists, provide enough shielding from radiation that life could persist beneath the waves? These are the questions driving the next generation of telescopes. The James Webb Space Telescope, the extremely large telescope being built in Chile, and future missions are all being designed with the capability to study the atmospheres of nearby exoplanets. If Proxima b has an atmosphere, we'll see it in the spectrum of light filtering through during transits, if we're lucky enough to observe it edge-on. Certain molecules leave unmistakable signatures. Oxygen, methane, ozone, water vapor. The presence of some combinations could suggest biological activity, a biosignature indicating that something is producing gases that wouldn't persist in a lifeless atmosphere. But Proxima b isn't alone. In 2019, astronomers announced the possible detection of a second planet, Proxima C. This one is farther out, orbiting every 5.2 years at a distance of about 1.5 astronomical units, 1.5 times the distance from Earth to the Sun. That places it beyond Proxima's habitable zone, likely too cold for liquid water on its surface. Initial estimates suggested it might be a super-Earth with a minimum mass of about 6 times Earth's. But the detection was tentative, based on tiny wobbles in the star's motion measured over years of observation. Not everyone is convinced it exists. Then in 2020, things got even more interesting. Another possible planet, Proxima D, this one even closer to the star than Proxima B, orbiting every 5.1 days with a mass of just a quarter of Earth's, smaller than any planet in our solar system except Mercury. If confirmed, Proxima D would be a fascinating object in its own right, though its proximity to the star, even closer than Proxima B, makes it an unlikely candidate for habitability. So we potentially have a 3-planet system. One small inner planet. One potentially habitable middle planet. One cold outer planet. Each world sculpted by the peculiar nature of orbiting a red dwarf. Each telling a different story about planetary formation, atmospheric evolution, and the possibilities for life beyond Earth. The star itself is a member of a triple star system. Alpha Centauri A and B are a binary pair, 2 sun-like stars orbiting each other every 80 years. They're prominent naked-eye objects, the third brightest star in the night sky, though it's really 2 stars so close together they appear as one without a telescope. Proxima orbits this pair at a distance of about 13,000 astronomical units, or 0.21 light-years. That's a fifth of a light-year away from its stellar companions. So distant that it takes 550,000 years to complete one orbit. Proxima is bound to the Alpha Centauri system, but just barely. Some astronomers have questioned whether it's truly gravitationally bound or simply passing through on an elongated orbit. Current measurements suggest it is bound, but only loosely. The 3 stars are traveling through space together, moving at about 25 kilometers per second relative to our Sun. In about 27,000 years, Proxima will be at its closest approach to our solar system, just 3.2 light-years away. Still impossibly far by human standards, but closer than now. The Alpha Centauri system has long captured human imagination. Countless science fiction stories have placed colonies, civilizations, even alien intelligences around these nearby stars. The pull is understandable. When we look up and wonder about reaching for the stars, these are the stars we'd reach for first. But that closeness is deceptive. 4.2 light-years might be the nearest star system, but it's still 40 trillion kilometers away. The fastest spacecraft humans have ever built, Voyager 1, is traveling at 17 kilometers per second and would take 73,000 years to reach Proxima if it were headed in that direction, which it isn't. But what if we could go faster? Much faster. The Breakthrough Starshot initiative proposes sending tiny spacecraft, not much bigger than postage stamps, accelerated by powerful laser beams to 20% the speed of light. At that velocity, they could reach Proxima Centauri in just 20 years. Imagine it. Launch a fleet of these light sails from Earth, accelerate them to a fifth of light speed, and 20 years later they're arriving at another star system, snapping pictures, gathering data, and transmitting it back to Earth. Another 4 years for the signal to arrive, but still, 24 years from launch to receiving the first images of another planetary system up close. The challenges are immense. You'd need a laser array kilometers across, generating gigawatts of power, firing with perfect synchronization to accelerate the sail. The sail itself would need to be incredibly thin and reflective, yet strong enough to withstand both the acceleration and the subsequent journey through interstellar space. Any dust grain encountered at 20% light speed would strike with the energy of a small bomb. The spacecraft would have no way to slow down, no way to orbit the planet. It would scream through the Proxima system in a matter of hours, gathering what data it could before hurtling off into the cosmic darkness beyond. But those hours could revolutionize our understanding. We could finally answer the question, what does Proxima B really look like? For now, we observe from afar, teasing out details through indirect methods. We watch the star wobble as the planet's gravity tugs on it, revealing the planet's mass and orbit. We monitor the star's brightness, hoping to catch the planet passing in front, a transit that would reveal the planet's size and potentially give us a glimpse of its atmosphere. Every observation adds another piece to the puzzle. The wobble method, called radial velocity, measures how the star moves toward and away from us as the planet orbits. When the planet is on one side of its orbit, it pulls the star slightly toward us. When it's on the other side, it pulls the star slightly away. We can't see this motion directly, but we can measure it through the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it recedes. Starlight shifts slightly bluer as the star moves toward us, slightly redder as it moves away. The shifts are tiny, less than a meter per second for Proxima B's effect on its star. Detecting that requires incredibly precise spectrographs and years of careful measurements to distinguish the planet's signal from the star's natural variability. The transit method is conceptually simpler but depends on geometry. If the planet's orbit is aligned just right from our perspective, it will periodically pass in front of the star, blocking a tiny fraction of the starlight. For Proxima b, we're not even certain it transits. The orbital inclination isn't perfectly edge-on from our viewpoint. Some observations suggested possible transits, but the results have been ambiguous. The star's own variability, those flares and spots rotating across its surface, makes it difficult to distinguish a genuine planetary transit from stellar noise. If we could confirm transits, the science we could do would be extraordinary. As the planet passes in front of the star, some starlight filters through the planet's atmosphere, if it has one. Different molecules absorb light at different wavelengths, imprinting their signatures on the spectrum. Water vapor absorbs in the infrared. Oxygen produces distinctive features. Methane, carbon dioxide, even more complex organic molecules, each leaves its mark. By comparing the spectrum during transit to the spectrum when the planet is not blocking the star, we can deduce what gases are present in the atmosphere. This is how we've studied hot Jupiters and other exoplanets. The James Webb Space Telescope has already started characterizing exoplanet atmospheres, detecting water vapor, carbon dioxide, even sulfur dioxide in the atmospheres of planets hundreds of light years away. Proxima b should be easier. It's so much closer, and every photon counts when you're trying to detect the chemical composition of an atmosphere from trillions of kilometers away. But there's a catch. Proxima Centauri is in the southern sky, not visible from most of the northern hemisphere. Observatories need to be located south of the equator for good views. The upcoming extremely large telescope in Chile's Atacama Desert will be perfectly positioned. With a primary mirror 39 meters across, 15 times the diameter of Hubble's mirror, it will gather enough light to potentially image Proxima b directly. Not just infer its existence from wobbles and dips in starlight, but actually see it as a distinct point of light separated from the glare of its star. Direct imaging of exoplanets is extraordinarily difficult. The planet is tiny compared to the star, and it emits or reflects a minuscule fraction of the star's light. Imagine trying to see a firefly next to a searchlight from 1,000 kilometers away. That's the challenge of direct imaging. Special techniques like coronagraphs, which block the star's light, and adaptive optics, which correct for atmospheric turbulence in real time, make it possible. Several exoplanets have been directly imaged, but they're mostly large, young planets orbiting far from their stars where the contrast is more manageable. Proxima b is small and orbits close to a dim star, easier than imaging an Earth-like planet around a Sun-like star, but still at the edge of our capabilities. Yet Proxima gives us one advantage: proximity. Because it's so close, the angular separation between the star and planet is larger than for more distant systems. That means less perfect your coronagraph needs to be to block the star while still seeing the planet. With the next generation of instruments, we might actually see that pale red dot against the blackness of space, pixels of light carrying information across 4.2 light-years of emptiness. What would we see if we could visit Proxima b? Close your eyes and imagine standing on the surface. The sky is a deep red twilight, the star hanging huge and ruddy on the horizon, if you're in the twilight zone between eternal day and eternal night. Or perhaps you're on the day side, where the star dominates the sky, smaller than our sun appears from Earth but noticeably larger and more menacing. The light is dim, more like late evening on Earth than midday, casting long shadows and bathing everything in that red glow. If you're lucky, there's an atmosphere, and you can see wisps of clouds moving overhead. The wind never stops in the twilight zone, driven by the temperature difference between the day side and night side. Gales roar across the surface, carrying heat from the eternal furnace to the eternal ice. You're standing in one of the few places where the temperature is moderate enough for liquid water. Behind you, toward the day side, the temperature climbs until rocks begin to glow. Ahead, toward the night side, the temperature plunges until carbon dioxide freezes out of the air as dry ice snow. But wait. The star is brightening. In seconds it grows perceptibly brighter, the red light intensifying. A flare. You shield your eyes, if you have eyes, or your sensors register the surge in ultraviolet and X-ray radiation sleeting through the thin atmosphere. The air itself begins to glow, ionized by the energy. Then, as quickly as it began, the flare subsides. The star returns to its sullen red glow. Another flare survived. Another dose of radiation absorbed. This happens regularly, maybe every few days or weeks. Any life here would need to cope with this, either by sheltering underground during flares, evolving incredible radiation resistance, or perhaps thriving in subsurface oceans where the water provides shielding. Water. That's the crucial question. Does Proxima b have water? Planets can form with substantial water content, delivered by comets and asteroids, or even incorporated during formation. Earth's oceans represent about 0.02% of our planet's mass. If Proxima b formed similarly, it could have oceans. But it could also have lost them. The intense stellar wind and flares, especially when Proxima was younger and more active, could have stripped away not just atmosphere but also the water vapor that accompanied it. Or perhaps Proxima b formed dry, closer to its star where water couldn't condense. Some models suggest Proxima b could be an ocean world, entirely covered in water hundreds of kilometers deep. Without continents, without land, just a global ocean beneath a thick atmosphere. The pressure at the bottom of such an ocean would be immense, perhaps transitioning to exotic high-pressure ice phases even in relatively warm water. Other models suggest a rocky desert, all water lost to space eons ago, leaving a barren wasteland baked on one side and frozen on the other. The truth probably lies somewhere in between, but we won't know until we look. And we are looking. Multiple observatories are pointed at Proxima Centauri, monitoring, measuring, gathering data. Every year, our instruments improve. Every year, our models become more sophisticated. Every year, we inch closer to answering the fundamental question: is there life on the nearest potentially habitable planet? The odds are uncertain. Proxima b faces serious challenges: tidal locking, intense radiation, powerful stellar winds, frequent flares. But it also has certain advantages. It's old, very old. Proxima Centauri is at least 4.8 billion years old, similar to the Sun. That means Proxima b, if it formed early, has had billions of years for life to emerge, adapt, evolve. On Earth, life appeared within a few 100 million years of the planet cooling enough to have liquid water. Simple single-celled organisms dominated for billions of years before complex life arose. If Proxima b has had even a fraction of that time with liquid water on its surface, could life have started? Extremophiles on Earth have shown us that life can adapt to almost any environment. Microbes thrive in acidic hot springs at pH levels that would dissolve human skin. They live in ice cores, dormant for millions of years and reviving when thawed. They survive in the vacuum of space, exposed to radiation levels that would kill any unprotected human. They metabolize sulfur, iron, even arsenic when traditional nutrients are unavailable. Life is persistent. Life is adaptable. Life finds a way, or at least it does on Earth. The question is whether Earth is typical or exceptional. Are we seeing the universal properties of life, or just the peculiarities of one Genesis event on one planet? Proxima b offers our best near-term chance to find out. If there's life there, it would be the most important discovery in human history. We would know, definitively, that we are not alone. That life is not unique to Earth but a common feature of the universe, arising wherever conditions permit. If there's no life there, despite billions of years and potentially habitable conditions, that would also be informative. It would suggest that the hurdles to abiogenesis, the origin of life from non-living matter, are higher than we think. That Earth might be special after all. But let's zoom out. Proxima Centauri is not just important because of its planets. It's important because it's part of our neighborhood, and studying it teaches us about the most common type of star in the galaxy. Red dwarfs make up about 70% of all stars in the Milky Way. Most stars are red dwarfs. If we want to understand planets, habitability, and the prospects for life in the galaxy, we need to understand red dwarf systems. For every Sun-like star with an Earth-like planet, there could be 10 red dwarfs with rocky worlds in their habitable zones. That's staggering. Our galaxy contains an estimated 200 to 400 billion stars. If 70% are red dwarfs, that's 140 to 280 billion red dwarf stars. If even a small fraction have rocky planets in their habitable zones, and Kepler data suggests about 15 to 20% might, that's 20 to 50 billion potentially habitable planets orbiting red dwarfs in our galaxy alone. 20 to 50 billion chances for life to emerge, evolve, and perhaps develop intelligence. Of course, potentially habitable doesn't mean inhabited. Many of those planets face the same challenges as Proxima b: tidal locking, flares, stellar winds. Some might lack atmospheres. Some might be too dry or too cold or too heavily irradiated. But even if only 1% of them actually host life, that's 200 to 500 million living worlds. In our galaxy, just our galaxy, the universe contains an estimated 2 trillion galaxies. Do the math. The numbers become almost meaningless. We're talking about so many potential abodes for life that the human mind can't comprehend it. And the nearest one is 4.2 light-years away, orbiting a dim red dwarf that nobody noticed until a century ago. Proxima Centauri's motion through space is also intriguing. It's not stationary, no star is. All stars orbit the galaxy, following paths determined by the distribution of mass in the Milky Way. Proxima is moving at about 100 kilometers per second relative to the galactic center, taking about 250 million years to complete one orbit. But relative to our Sun, it's moving much slower, about 25 kilometers per second. That's why it's been our nearest neighbor for thousands of years and will remain so for many thousands more. In fact, Proxima Centauri wasn't always the nearest star, and it won't always be. Stars drift relative to each other as they orbit the galaxy. Computer simulations tracking stellar motions backward and forward in time revealed that about 32,000 years ago, a different star was closer to us. Ross 248, a red dwarf in the constellation Andromeda, passed within about 3.3 light-years of the Sun. And in about 33,000 years, Ross 248 will return to claim the title of nearest star again, briefly dipping to 3.1 light-years away before receding. But for now, and for most of recorded human history, Proxima holds the crown. The name Proxima Centauri itself is telling. Proxima is Latin for nearest. Centauri indicates its location in the constellation Centaurus, the Centaur. It's formally designated Alpha Centauri c, the third component of the Alpha Centauri system. But most astronomers simply call it Proxima, acknowledging its status as the closest star to our Sun. That closeness has made it a target for all sorts of observations over the decades. We've measured its mass, radius, temperature, luminosity, rotation period, magnetic field strength, and chemical composition. We know it rotates slowly, taking about 83 days to complete one rotation. That's much slower than the Sun's 25-day rotation, but typical for red dwarfs. The slow rotation affects its magnetic field, which is generated by dynamo processes in the star's interior. That magnetic field, in turn, drives the stellar activity, the flares and spots and prominences that make Proxima such a dynamic object. The star's metallicity, the abundance of elements heavier than hydrogen and helium, is slightly higher than the Sun's. About 1.3 times solar metallicity. That might not sound significant, but it tells us about the star's formation history. Stars form from clouds of gas and dust, and the composition of that material reflects the history of previous generations of stars. Elements heavier than helium are forged in stellar cores and dispersed when stars die. Proxima's elevated metallicity suggests it formed from material enriched by earlier supernovas, indicating it's not a first-generation star but part of a later generation, possibly formed around the same time as the Sun. The spectral class of Proxima Centauri is M5.5v. Let's break that down. M indicates a red dwarf, the coolest and smallest main sequence stars. The number 5.5 specifies where it falls within the M class. M0 stars are the hottest and largest red dwarfs, while M9 stars are the coolest and smallest, approaching the boundary with brown dwarfs. The V indicates it's a main sequence star, fusing hydrogen into helium in its core. And the lowercase e indicates emission lines in its spectrum, characteristic of stellar activity like flares. That little e is a warning sign, telling astronomers that this star is active and variable. Variable stars are stars whose brightness changes over time. Proxima's variability is dramatic. Its baseline luminosity is already extremely low, but during flares, it can brighten by factors of 10 or more for seconds to minutes. Longer-term variations also occur, driven by star spots, regions of intense magnetic field that are cooler than the surrounding surface, like sunspots on the Sun but proportionally much larger. As Proxima rotates, these spots come into view and then rotate out of view, causing the star's brightness to change by up to 10% over the 83-day rotation period. Observing Proxima requires patience and precision. Because it's so faint, you need large telescopes with sensitive detectors. Because it's so active, you need to monitor it continuously to separate the signal of any planets from the noise of stellar activity. The discovery of Proxima b required years of radial velocity measurements, carefully accounting for star spots and flares, to tease out the 11.2-day orbital signal. Even now, some of the possible additional planets remain controversial because the signals are at the edge of detectability. But controversy drives science forward. Every claim needs to be tested, verified, refined. More observations with better instruments will eventually settle the question of how many planets Proxima has and what they're really like. And if Proxima c is confirmed, it opens up new possibilities. A cold outer planet could potentially have moons, icy moons warmed by tidal heating, perhaps harboring subsurface oceans like Jupiter's Europa or Saturn's Enceladus. That would be a different kind of habitability, not on the planet itself but on its satellites. The study of exomoons is just beginning. We've detected tantalizing hints of moons around distant exoplanets, but confirming them is extraordinarily difficult. A moon orbiting a planet orbiting a star produces an incredibly complex signal. But Proxima's closeness might make it possible. With enough observations, we might not only detect moons but also characterize them, determining their sizes, masses, and potentially even their compositions. Think about the implications. A system with 3 planets and potentially multiple moons, all within 4 light-years of Earth. Each object telling a different story about planetary formation, atmospheric evolution, and the possibilities for life. Proxima b in the habitable zone. Proxima d close to the star, tidally locked and baking. Proxima c far from the star with potential icy moons. It would be a cosmic laboratory, a place where we could study planetary science across a range of environments, all accessible, at least in principle, with future missions. And accessibility matters. Yes, 4.2 light-years is incredibly far by human standards, but it's the closest we've got. Any interstellar mission, whether robotic probes or, in the distant future, crewed vessels, will target the Alpha Centauri system first. It's the obvious choice. Prove the technology at Proxima, and then you can reach for more distant stars. Fail at Proxima, and the dream of interstellar travel remains just that, a dream. The engineering challenges of such a mission are sobering. Even traveling at 10% the speed of light, currently impossible with any known propulsion system, would require 4 decades to reach Proxima. The spacecraft would need to survive 40 years in the harsh environment of interstellar space, enduring cosmic rays, micrometeoroids, and the extreme cold. It would need to carry enough power to operate for 4 decades and then transmit data back across interstellar distances. Solar panels won't work, the sun is too far away. Nuclear power sources degrade over time. The spacecraft would be functionally autonomous, making decisions without input from Earth since communication has a 4-year lag. But assume we solve those problems. Assume we send a probe, and 44 years after launch, 40 years of travel plus 4 years for the signal to return, we receive the first images. What would we see? Would we see clouds in Proxima B's atmosphere? Would we see oceans glinting in the red light? Would we see cities? Unlikely, but not impossible. Intelligence is rare on Earth, arising only once in 4 billion years of evolutionary history. If life on Proxima B exists, it's probably microbial. But we don't know. We can't know until we look. The discovery of life, even microbial life, on Proxima B would revolutionize biology. We could compare its biochemistry to Earth's. Does it use DNA? RNA? Something completely different. Does it use the same amino acids, the same genetic code? Or has it evolved an entirely independent solution to the problems of storing and processing information? If Proxima B's life uses DNA with the same codons as Earth life, that would be extraordinary, perhaps suggesting panspermia, the idea that life can spread between planets or even star systems, hitching rides on meteorites or comets. If its biochemistry is completely alien, that would tell us that life can arise through multiple independent pathways, that there's no single blueprint written into the laws of physics. Either answer would be profound. Either way, we would learn something fundamental about our place in the universe. For now, Proxima Centauri remains a point of light in our telescopes, a wobble in our data, a set of questions waiting for answers. But every year those answers come closer. The James Webb Space Telescope is observing it. The extremely large telescope will study it when it comes online. Future missions are being planned. And every observation brings us closer to understanding whether our nearest neighboring star system is home to life. 4.24 light-years. In cosmic terms, that's our front yard. The distance is so small that if the Milky Way were the size of North America, the Sun and Proxima Centauri would be just 4 meters apart, close enough to hold a conversation without shouting. Yet crossing that gap remains one of the greatest challenges facing humanity. But challenges are what we do. We went to the moon when the computers guiding us had less power than a modern cell phone. We've sent probes to every planet in the solar system and beyond. Voyager 1 is currently 23 billion kilometers from Earth, still transmitting data after 46 years of operation. If we could build spacecraft that last nearly half a century and cross the solar system, we can build spacecraft that cross to another star. It's a matter of will, resources, and time. And perhaps, when we get there, we'll find we're not alone. Perhaps beneath the red skies of Proxima B, something lives. Something that started as simple chemistry and evolved over billions of years into something complex. Something that processes information, responds to its environment, reproduces. Whether that something is a microbe clinging to life in subsurface ice or something more complex, it would be life. And finding it would mean that in a universe of 2 trillion galaxies, each with hundreds of billions of stars, the universe is alive. Not barren. Not empty. But teeming with biology, waiting to be discovered. Proxima Centauri holds that promise. It's not the brightest star, not the most massive, not the most spectacular. But it's ours. It's the closest. It's where we'll take our first steps beyond the solar system. It's where we'll learn whether Earth is unique or just one of countless worlds harboring life. It's where the future begins. 4.24 light-years away, a dim red star burns steadily, as it has for billions of years, as it will for trillions more. Around it, planets orbit in the darkness. On at least one of those planets, conditions might be right for life. We don't know yet. But we will. Proxima Centauri is waiting. And so are we. The search continues. Every new exoplanet discovered adds to our understanding. Every refinement in our models brings clarity. Every technological advancement brings Proxima closer, not in distance, but in accessibility. We've gone from not knowing it existed in 1915 to detecting its planets in 2016 to planning missions to visit it in the coming decades. That's the trajectory of human exploration. First we discover. Then we study. Then we go. Proxima Centauri is more than a star. It's a destination. It's a question. It's a challenge. And it's the closest thing we have to another chance at finding life. In a galaxy of 100 billion stars, in a universe of 2 trillion galaxies, we start here. With the nearest one. With the faintest one. With the one that could change everything. 4.24 light years. Not far in cosmic terms. An eternity in human terms. But the journey of 1 trillion kilometers begins with a single step. And we've already taken that step. We've pointed our telescopes at Proxima. We've detected its planets. We've begun to understand its nature. The next step is to go there. And when we do, whether it's a tiny light sail screaming through the system in a matter of hours, or a larger probe capable of orbiting and studying the planets, or, in the distant future, humans themselves making the crossing, we'll finally know. We'll finally see, with our own instruments or our own eyes, what Proxima Centauri and its worlds really are. Until then, we watch. We wait. We wonder. And we prepare. Because Proxima Centauri isn't just the nearest star. It's the next frontier. And the future of humanity may well be written under its red light. The chemistry of Proxima Centauri reveals secrets about stellar evolution that challenge our textbooks. While most stars burn hydrogen in a radiative core surrounded by a convective envelope, red dwarfs flip this script entirely. Proxima is fully convective from core to surface. Imagine a pot of boiling water, but that pot is the size of a star. Hot plasma rises from the core, cools near the surface, and sinks back down. This churning motion means that unlike the Sun, which keeps its helium-enriched core separated from its hydrogen-rich outer layers, Proxima constantly mixes its fuel. Fresh hydrogen from the outer layers gets cycled down into the fusion zone. Spent helium gets distributed throughout the star. This is why red dwarfs live so long. They don't just burn the hydrogen in their cores, they can access nearly all their hydrogen fuel over their lifetimes. The magnetic implications of full convection are dramatic. The Sun generates its magnetic field through a mechanism called the solar dynamo, which depends on the interaction between the radiative and convective zones. Proxima doesn't have that setup, yet it generates a magnetic field thousands of times stronger than Earth's. The mechanism is different, less understood, and apparently far more violent. Those massive flares we discussed? They're the result of magnetic field lines twisting, reconnecting, and releasing stored energy in explosive bursts. The star's surface is constantly roiling with magnetic activity, creating star spots that would dwarf any sunspot, generating prominences that extend hundreds of thousands of kilometers into space. Spectroscopic observations have revealed the presence of strong molecular bands in Proxima's spectrum. Titanium oxide, vanadium oxide. These molecules can only exist in the relatively cool atmosphere of the star, where temperatures drop below 3000 Kelvin. On hotter stars like the Sun, these molecules would be torn apart by the heat. Their presence is a signature, a fingerprint that immediately identifies a star as a cool red dwarf. When astronomers take spectra of distant stars, finding these molecular bands tells them they're looking at an M dwarf even before they measure anything else. The ultraviolet emission from Proxima is particularly interesting for astrobiology. While the visible light output is meager, Proxima emits a significant fraction of its energy in ultraviolet wavelengths. This UV radiation has contradictory effects on potential life. On one hand, it's damaging, breaking chemical bonds and causing mutations. On the other hand, UV radiation may have been crucial for prebiotic chemistry on early Earth, driving reactions that created complex organic molecules from simpler precursors. So Proxima b receives less total energy than Earth, but a higher proportion of it arrives as UV. Whether this helps or hinders the origin of life remains an open question. Radio observations have detected Proxima Centauri as well. The star emits radio waves generated by its magnetic activity, particularly during flares. These radio bursts can be incredibly bright, making Proxima detectable by radio telescopes despite its proximity. Some searches for extraterrestrial intelligence have pointed radio telescopes at Proxima, listening for any artificial signals that might indicate a technological civilization. So far, nothing. But the absence of evidence is not evidence of absence, and the search continues. The metallicity we mentioned earlier, that 1.3 times solar abundance of heavy elements, affects planet formation in subtle ways. Higher metallicity correlates with a higher probability of planet formation in sun-like stars. The logic is straightforward: more heavy elements mean more material to build rocky planets. But the relationship is less clear for red dwarfs. Proxima clearly has planets despite being a small star. Whether its elevated metallicity made planet formation easier or whether red dwarfs commonly form planets regardless of metallicity is still debated. Studies of other red dwarfs with confirmed planets will eventually answer this question. Proxima B's composition remains speculative, but we can make educated guesses based on planetary formation theory and observations of other small planets. If it formed beyond the ice line, the distance from the star where water ice can exist, and then migrated inward, it might have started as an icy planet that lost most of its volatiles as it approached the star. Alternatively, it could have formed in place from rocky material, never acquiring a substantial water inventory. Or it could be somewhere in between, a world with a significant water content but not a pure ocean planet. The density would tell us a lot, but we need to observe a transit to measure the planet's size and calculate its density. No confirmed transits means no density measurement means lots of uncertainty. The orbital dynamics of the Proxima system are stable, at least according to computer simulations. You can throw 3 planets into the system with the observed masses and orbits, run the simulation forward for billions of years, and they stay in place. No collisions. No ejections. Just stable orbits maintained by the gravitational interactions between the planets and their star. This stability is reassuring because it suggests the system has existed in its current configuration for a long time, giving any potential life ample time to evolve. But orbital resonances could add complexity. When planets orbit with periods that are simple ratios of each other, they can lock into resonances that either stabilize or destabilize their orbits. Jupiter's moons Europa, Ganymede, and Callisto are in a resonance where their orbital periods are in a 4:2:1 ratio. This resonance helps maintain their orbits and drives tidal heating that keeps Europa's subsurface ocean liquid. If Proxima's planets are in resonances, it could affect their orbital stability and potentially drive geological activity through tidal heating. Tidal heating on Proxima b would be another energy source beyond stellar radiation, potentially powering volcanism or maintaining a molten core that generates a protective magnetic field. The historical path to discovering Proxima b is worth appreciating. The first hints came in 2000 when a team observed periodic variations in Proxima's radial velocity. But the signal was weak, and the star's intrinsic variability made confirmation difficult. It took 16 more years of observations with increasingly sensitive instruments before astronomers felt confident enough to announce the planet's existence. 16 years of patient data collection, of ruling out false positives, of accounting for stellar activity. That's the reality of exoplanet science. Most discoveries require years of meticulous work before anything can be confirmed. The announcement in August 2016 made headlines worldwide. Earth-like planet found orbiting nearest star. The media coverage was intense, and public interest was enormous. People wanted to know, could we go there? Is there life? When will we know? Those questions persist today, and the answers are slowly coming into focus. Other red dwarf systems provide context. TRAPPIST-1, about 40 light-years away, has 7 rocky planets, 3 of them in the habitable zone. Discovered in 2017, the TRAPPIST-1 system showed that red dwarfs can host not just one potentially habitable planet, but multiple worlds where conditions might permit liquid water. The planets are packed tightly around their star, all 7 orbiting closer than Mercury orbits the Sun. They're likely tidally locked. They're subjected to stellar flares. But they exist, and they're giving astronomers a wealth of data about planetary atmospheres, compositions, and habitability around red dwarfs. Barnard's star, about 6 light-years away, also has at least one planet, though its existence has been questioned. At about 3 times Earth's mass, Barnard's star B orbits beyond its star's habitable zone in a 233-day orbit. It's probably frozen. But its discovery, or potential discovery, adds to the growing evidence that planets around red dwarfs are common. Ross 128b, orbiting a quiet red dwarf 11 light-years away, is particularly intriguing. Unlike Proxima, Ross 128 is not a flare star. It's calm, stable, emitting minimal UV radiation and no significant flares. Its planet, Ross 128b, orbits every 10 days with a mass about 40% greater than Earth's. If you could choose between Proxima b and Ross 128b based purely on stellar behavior, you'd pick Ross 128b every time. The calm star provides a stable environment where atmosphere retention and surface habitability are much more likely. But Ross 128b is farther away, making detailed study harder. The diversity of red dwarf planets is becoming apparent. Some orbit active flare stars. Some orbit quiet stars. Some are larger than Earth. Some are smaller. Some orbit in the habitable zone. Some orbit too close or too far. Each system teaches us something new, and Proxima, being the closest, offers the best opportunity for detailed characterization. Stellar age dating is tricky for red dwarfs. With sun-like stars, astronomers can use several techniques: examining the rotation rate, measuring the abundance of lithium, studying asteroseismology, to estimate age. Red dwarfs are more difficult. They evolve so slowly that young red dwarfs and old red dwarfs look nearly identical. Proxima's age is estimated at around 4.85 billion years, similar to the Sun, based primarily on its membership in the Alpha Centauri system and the assumption that all 3 stars formed together. But uncertainty remains. Proxima could be older or younger, and without better age constraints, we can't say definitively how long its planets have existed or how much time life has had to emerge. The stellar wind of Proxima deserves more attention. Stellar winds are streams of charged particles, protons, electrons, heavier ions, ejected from the star's outer atmosphere. Our Sun's solar wind flows outward at a few hundred kilometers per second, carrying away about 1 billion kilograms of material every second. That sounds like a lot, but over the Sun's lifetime, it amounts to a negligible fraction of the star's mass. Proxima's wind is denser and faster, estimated at 10 to 100 times the mass loss rate of the solar wind. Over billions of years, this wind has eroded planetary atmospheres, stripped away water, and fundamentally altered the evolution of any planets in the system. Planetary magnetic fields provide protection against stellar winds, but generating a strong magnetic field requires specific conditions. The planet needs a molten, electrically conducting core, typically iron, and sufficient rotation to drive dynamo action. Earth's magnetic field results from convection in its liquid outer core, driven by heat from the core and the planet's rotation. If Proxima b has a similar internal structure and rotates quickly enough despite tidal locking, it could maintain a magnetic field. If not, the stellar wind would gradually strip its atmosphere over hundreds of millions of years. But there's a caveat. Recent research suggests tidally locked planets might generate magnetic fields through a different mechanism. If the planet has a subsurface ocean or a partially molten mantle, tidal forces from the star could drive circulation in these layers, potentially generating a magnetic field even without rapid rotation. This is speculative, but it offers hope that tidally locked planets around red dwarfs might be more habitable than previously thought. The concept of a habitable zone itself is evolving. Traditionally defined as the region where liquid water can exist on a planet's surface, the habitable zone is now understood to be more nuanced. Surface water requires not just the right temperature but also sufficient atmospheric pressure. Too little atmosphere, and water boils or sublimates. Too much, and the greenhouse effect can create a runaway situation, turning the planet into a Venus-like hellscape. The composition of the atmosphere matters too. Carbon dioxide is a greenhouse gas that can warm a planet, but too much and it becomes toxic. Oxygen is essential for complex life as we know it, but it's reactive and wouldn't persist in an atmosphere without a biological source replenishing it. Proxima b sits right in the middle of the traditional habitable zone, receiving 65 to 90% of the stellar flux that Earth receives, depending on the orbital eccentricity. But traditional habitable zone calculations assume a planet like Earth, a certain size, a certain atmosphere, a certain rotation rate. Proxima b likely differs in all these respects, so the traditional habitable zone may not apply. Detailed climate models that account for tidal locking, atmospheric composition, and stellar activity are needed to assess true habitability, and those models are being refined with every new observation. The question of eccentricity is interesting. Proxima b's orbit is not perfectly circular. Early measurements suggested an eccentricity of about 0.1, meaning the planet's distance from the star varies by about 10% over the course of its 11-day orbit. A circular orbit would have an eccentricity of 0. Earth's eccentricity is about 0.017, nearly circular. An eccentricity of 0.1 means Proxima b experiences slightly more extreme temperature variations as it moves closer to and farther from its star. But over an 11-day orbit, these variations average out. Unless the planet has an atmosphere to trap heat, the short orbital period means the temperature quickly adjusts to the changing distance. Atmospheric modeling has explored various scenarios. One study assumed an Earth-like atmosphere, nitrogen and oxygen with trace amounts of other gases. The result: tidal locking creates extreme temperature gradients, but with sufficient atmospheric circulation, the entire planet could maintain temperatures suitable for liquid water in a broad twilight band. Another study assumed a thicker, CO2-dominated atmosphere like early Mars might have had. The result: a runaway greenhouse effect on the day side and extreme cold on the night side, with only a narrow habitable region. Yet another study modeled a thin atmosphere. The result: no heat redistribution, extreme temperatures, no liquid water. The conclusion: everything depends on the atmosphere, and we won't know what Proxima b's atmosphere is like until we observe it directly. The search for biosignatures focuses on atmospheric gases that would indicate biological activity. Oxygen is the classic example. Earth's atmosphere is 21% oxygen, but this is not an equilibrium state. Oxygen is reactive, constantly being removed from the atmosphere by reactions with rocks, gases, and organic matter. Without photosynthesis continuously replenishing it, Earth's atmospheric oxygen would disappear in just a few million years. So if we detect significant oxygen in Proxima b's atmosphere, it suggests something is producing it, potentially life. But there are false positives. Photodissociation of water vapor by UV radiation can produce oxygen without biology. Distinguishing biological oxygen from abiotic oxygen requires looking at other gases too. Methane is another biosignature gas. On Earth, methane is produced by both geological processes and biological activity, particularly methanogenic bacteria. In an oxygen-rich atmosphere, methane reacts and breaks down quickly, so its presence alongside oxygen suggests ongoing biological production. Detecting both oxygen and methane together would be a strong biosignature, harder to explain through abiotic processes alone. Phosphine made headlines in 2020 when it was tentatively detected in Venus's atmosphere. Phosphine is produced by life on Earth and is difficult to create abiotically, making it a potential biosignature. The Venus detection remains controversial, but the idea is sound: find gases that life produces easily but that abiotic chemistry struggles to create in large quantities. If we detect phosphine, dimethyl sulfide, or certain organic molecules in Proxima b's atmosphere, the case for life becomes stronger. But absence of biosignatures doesn't mean absence of life. Early Earth had life for hundreds of millions of years before oxygenic photosynthesis evolved and oxygenated the atmosphere. During that time, Earth's atmosphere contained little oxygen and few detectable biosignatures. A planet could be teeming with microbial life and still appear barren to our telescopes if that life hasn't evolved to produce detectable gases in large quantities. The James Webb Space Telescope, operational since 2022, has the capability to study exoplanet atmospheres through transmission spectroscopy during transits. For planets that do transit, JWST can detect atmospheric molecules by observing how the planet's atmosphere absorbs starlight at specific wavelengths. JWST has already characterized several hot Jupiters and warm Neptunes, detecting water vapor, methane, and even hints of clouds. But Proxima b is a challenge. If it transits, which remains uncertain, the signal would be small, requiring many transits observed over months or years to build up enough data. And Proxima is faint, so gathering sufficient photons takes time. Ground-based extremely large telescopes coming online in the next few years offer another approach. With mirrors 30 to 40 meters across, they will collect enough light to potentially image Proxima b directly in infrared wavelengths. Infrared is ideal because the contrast between the star and planet is more favorable than in visible light. The star emits less infrared relative to its visible output, while a potentially warm planet emits thermal radiation in infrared. Direct imaging would allow us to study the planet's thermal emission, revealing surface temperature, atmospheric composition, and potentially even surface features if the resolution is sufficient. Imagine obtaining an image of Proxima b with enough resolution to distinguish the day side from the night side, to see gradients in temperature, to detect continents and oceans if they exist. That's the dream, and with the next generation of telescopes, it moves from dream toward possibility. Not certainty, the technical challenges are formidable, but possibility. The concept of panspermia adds another layer to the Proxima b story. Panspermia is the hypothesis that life can spread from one planet to another or even between star systems. Microbes could survive inside rocks ejected from a planet by asteroid impacts, spending millions of years in space before landing on another world. Within a star system, this transfer is plausible. Mars and Earth have exchanged material over the solar system's history. Some meteorites found on Earth originated on Mars, blasted off that planet by impacts, and eventually captured by Earth's gravity. If life existed on Mars, it could have hitched a ride. Between star systems, panspermia is much harder. The distances are vast, and interstellar space is hostile, vacuum, radiation, extreme cold. But microbes are tough. Laboratory experiments have shown that some bacteria can survive vacuum and radiation doses far exceeding what they'd experience during interstellar travel. If they're shielded inside rock, protected from the worst of the radiation, they could theoretically survive. The journey would take millions of years at typical interstellar speeds, but bacterial spores can remain dormant for extremely long periods. If panspermia between the Sun and Proxima Centauri has occurred, it would mean life on Proxima b could be related to life on Earth. We'd share a common ancestor, either because life originated on one world and spread to the other, or because both were seeded by material from a third source. The implications would be staggering. Finding DNA-based life on Proxima b with genetic sequences similar to Earth organisms would be direct evidence of panspermia. Conversely, finding life with completely alien biochemistry would prove that life can arise independently through different pathways. The philosophical implications of finding life on Proxima b extend beyond science. For most of human history, we've wondered whether we're alone. Religions, philosophies, myths, and stories have grappled with this question. Finding even microbial life on the nearest potentially habitable planet would answer that question definitively. We're not alone. Life exists elsewhere. And if it exists on the nearest potentially habitable world, it likely exists on countless others. This raises the Fermi paradox in a new light. If life is common, why haven't we detected any signs of intelligent civilizations? The galaxy is billions of years old. If intelligent life commonly arises, some civilizations should be millions of years ahead of us technologically. Where are they? Why haven't we detected their radio signals, their megastructures, their spacecraft? The paradox has many proposed solutions. Perhaps intelligent life is rare. Perhaps civilizations self-destruct before becoming spacefaring. Perhaps they're out there but intentionally avoiding contact. Or perhaps interstellar distances are simply too vast, and civilizations remain isolated in their home systems. Finding life on Proxima b wouldn't resolve the Fermi paradox, but it would inform it. If Proxima b has only microbial life despite billions of years, it suggests the leap from simple to complex life is difficult. Earth took about 2 billion years to go from single-celled organisms to multicellular life, and another billion years before animals and plants colonized the land. If that timeline is typical, most life-bearing planets would have only microbes. Intelligence might be extraordinarily rare, arising on perhaps 1 in a billion living worlds. That would explain the Great Silence. Conversely, if Proxima b has complex life or even intelligence, the Fermi paradox becomes more acute. Why haven't we heard from them? Perhaps we haven't been listening long enough. SETI, the search for extraterrestrial intelligence, has been operating for only about 60 years, and it has surveyed only a tiny fraction of the sky with limited sensitivity. Detecting a signal requires that someone is transmitting, that we're listening at the right frequency, at the right time, and that the signal is strong enough to distinguish from background noise. The odds of success are low unless civilizations are actively trying to communicate with their neighbors. Breakthrough Listen, a privately funded SETI initiative, has been targeting the Alpha Centauri system, including Proxima, with radio telescopes. If there's a technological civilization on Proxima b broadcasting radio signals, Breakthrough Listen would have a good chance of detecting it. So far, nothing conclusive has been found, though analyzing the vast amounts of data collected is ongoing. Silence doesn't mean absence, it just means we haven't detected anything yet. The possibility of sending a message to Proxima has been considered. In 2016, shortly after Proxima b's discovery, a project called A Simple Response to an Elemental Message transmitted a radio signal toward Proxima Centauri. The message contained information about Earth, humanity, and mathematics, intended as a greeting if anyone is listening. The signal will arrive at Proxima in 2020, except, of course, it already arrived in 2020, for years after transmission. If there's anyone there to receive it, and if they respond immediately, we'd receive their reply in 2024. That deadline has passed. No response. But it was always a long shot. The ethics of messaging extraterrestrial intelligence are debated. Some argue we shouldn't advertise our presence until we know what's out there. Others argue that any civilization capable of interstellar travel already knows we're here, so sending messages makes no difference. And some say we have a duty to reach out, to make contact, to join the galactic community if one exists. These debates will intensify as we learn more about nearby worlds and as our technology for sending and receiving interstellar messages improves. Proxima Centauri's motion through the galaxy carries it and its planets through different regions of space over millions of years. The galactic environment is not uniform. Some regions have higher densities of interstellar gas and dust. Some regions experience higher rates of nearby supernovas. These environmental factors could influence the planets over long timescales, potentially seeding them with organic molecules from interstellar clouds or subjecting them to radiation from nearby stellar explosions. About 2 million years ago, Proxima Centauri passed through a region of space that might have exposed it to increased cosmic ray flux. Cosmic rays are high-energy particles, mostly protons, accelerated to nearly the speed of light by supernova remnants and other energetic events. When they strike an atmosphere, they create cascades of secondary particles, increasing radiation levels at the surface. If Proxima b experienced a significant uptick in cosmic ray bombardment, it could have affected any life present, either by increasing mutation rates or by damaging ecosystems. Life is resilient, but there are limits. In the next 33,000 years, Proxima will reach its closest approach to our Sun, at 3.2 light-years. After that, it will begin receding, its distance gradually increasing as it continues its journey around the galaxy. In a few 100,000 years, it will no longer be the nearest star, ceding that title to other passers-by. But for our generation and many generations to come, Proxima is the neighbor, the target, the destination. The cultural impact of discovering Proxima b's status cannot be understated. Science fiction has long imagined journeys to Alpha Centauri. Arthur C. Clarke's The Songs of Distant Earth features a colony on a planet in the Alpha Centauri system. The movie, Avatar, takes place on Pandora, a moon orbiting a gas giant in the Alpha Centauri system. The discovery of a real, potentially habitable planet at Proxima breathed life into these stories, transforming them from pure imagination into something almost plausible. We now know there's a planet there. We don't know if it's habitable, but the mere fact of its existence changes how we think about the future. Educational initiatives have seized on Proxima b as a teaching tool. Students around the world have studied the discovery, learning about radial velocity methods, habitable zones, and exoplanet science. The concept of a potentially habitable world just 4 light-years away captures imaginations in a way that more distant exoplanets cannot. It's close enough to seem almost reachable, even if the reality is far more difficult. Artists, too, have been inspired. Countless illustrations depict Proxima b, red skies, alien landscapes, towering clouds illuminated by the dim star. These artworks are speculative, based on our limited knowledge, but they help us visualize what might be out there. They make the abstract concrete, turning data points and orbital parameters into worlds we can almost see. The technological spin-offs from Proxima research are already appearing. The precision spectrographs developed to detect small planets around nearby stars are finding applications in other fields. The adaptive optics systems designed to image exoplanets directly are improving ground-based astronomy across the board. The long-duration, high-stability instruments required for years-long radial velocity campaigns are pushing the boundaries of engineering. Science drives technology, and technology enables new science in a virtuous cycle. Commercial interest in interstellar exploration is growing. Private companies are beginning to invest in concepts for interstellar probes, recognizing that while government funding is uncertain, private ventures can move more quickly. Breakthrough Starshot, funded by philanthropists including Yuri Milner and backed by Stephen Hawking before his death, represents a serious attempt to develop the technologies needed for interstellar flight. Even if their initial timeline proves overoptimistic, the effort is advancing propulsion, materials science, and miniaturization technologies that will have broader applications. Legal and governance questions arise as well. If we send a probe to Proxima, who decides what it does? Who owns any discoveries? If we find life, what are our responsibilities toward it? The Outer Space Treaty of 1967 governs activities in space, but it was written with the solar system in mind, not interstellar exploration. International agreements will need to be updated as interstellar missions transition from science fiction to science planning. The psychological impact on humanity of confirming life elsewhere would be profound. Suddenly, Earth is not the only living world. We are not unique. Our problems, our conflicts, our daily concerns would be recontextualized. Some fear this would diminish humanity, making us feel small and insignificant. Others believe it would unite us, highlighting our common identity as Earthlings in a universe of diverse life. The truth would likely be complex, varying across cultures and individuals. Religious perspectives on extraterrestrial life vary widely. Some traditions have no trouble accommodating life elsewhere. After all, if a deity created the universe, why would Earth be the only living world? Others have theological frameworks that emphasize humanity's unique status, and discovering aliens would require reinterpretation. But religions have adapted to paradigm shifts before. The realization that Earth orbits the Sun, not vice versa, was controversial but eventually accepted. The discovery of deep time and evolution challenged literal interpretations of creation but led to more nuanced theologies. Life on Proxima b would be another such shift, momentous but ultimately manageable. The timeline for answering the big questions about Proxima b remains uncertain. Within the next decade, we should know whether it transits and, if so, gain insights into its atmosphere. Within 20 to 30 years, direct imaging might reveal surface features. Within 50 years, dedicated interstellar probes could be under development. Within a century, those probes might arrive. That's optimistic, but not impossible. A century seems like a long time, but consider, a century ago, We had barely begun exploring Antarctica, the airplane was a novelty, and space travel was pure fantasy. A lot can happen in 100 years. For now, Proxima Centauri and its planets remain at the frontier of our knowledge, tantalizing hints of worlds that might, just might, harbor life. Every observation, every data point, every model brings us incrementally closer to understanding. And one day, perhaps within the lifetimes of people reading this, we will know. We will have imaged Proxima b, characterized its atmosphere, and determined once and for all whether we are alone or surrounded by life. That day is coming. And when it arrives, our species will have crossed a threshold from which there is no return. We will be a species that knows its place in a living cosmos. Until then, the red dwarf burns on, patient and eternal, keeping its secrets. And we, restless and curious, continue to watch, to listen, and to dream of what might lie beneath those alien skies, 4.2 light-years away. The gravitational influence of Alpha Centauri A and B on Proxima's planetary system introduces fascinating long-term dynamics. While Proxima orbits these two stars at a distance of about 13,000 astronomical units, their combined gravitational pull creates subtle perturbations in the orbits of Proxima's planets over millions of years. These perturbations are tiny on human timescales but accumulate over geological epochs. Computer simulations tracking planetary orbits millions of years into the future show that while the system remains stable, the orbital parameters slowly shift. Eccentricities vary. Inclinations precess. The planets undergo cycles that could affect their climates over vast stretches of time. This gravitational coupling means Proxima's planets don't exist in isolation. They're part of a larger dynamical system, influenced by stellar companions over a fifth of a light-year away. On Earth, long-term climate cycles called Milankovitch cycles result from variations in our orbital parameters caused by gravitational interactions with other planets. These cycles operate on timescales of tens to hundreds of thousands of years, driving ice ages and warm periods. Proxima b likely experiences analogous cycles, though driven by the distant dance with Alpha Centauri A and B. Understanding these cycles requires modeling that spans not just thousands but millions of orbits, tracking how gravitational perturbations reshape the planetary system over deep time. The possibility of additional undiscovered planets in the Proxima system remains very real. Current detection methods have sensitivity limits. A smaller planet farther from the star would produce weaker signals, harder to distinguish from stellar noise. There could be Mars-sized worlds, ice giants, even additional terrestrial planets in different orbits that we simply haven't detected yet. Each new instrument, each improvement in data analysis techniques, pushes those detection limits lower. The possibility that Proxima hosts 4, 5, or even more planets cannot be ruled out. Small planets in particular are difficult to detect. Consider that in our solar system, Mercury has just 5% of Earth's mass. A Mercury analog around Proxima would produce a radial velocity signal so small that detecting it would require instrument precision beyond current capabilities. Yet small planets like Mercury can have interesting properties: extreme temperature contrasts, unusual geological features, perhaps even tenuous exospheres. We might be missing an entire population of small inner planets around Proxima simply because our telescopes aren't sensitive enough yet. The orbital plane of Proxima's planets relative to our line of sight determines whether we see transits. If the orbital plane is tilted significantly, the planets never pass in front of the star from our perspective. Early observations suggested Proxima b's orbit might be inclined at an angle that makes transits unlikely, though not impossible. Later observations provided tentative evidence of a possible transit, but the signal was ambiguous. Confirming transits requires catching multiple events to ensure they're real and not just stellar variability mimicking a transit. The 11-day orbital period helps. You can observe many orbits in a single observing season, but only if the planet actually transits. Grazing transits add another complication. If the orbital inclination is just right, or wrong, depending on perspective, the planet might just barely skim across the edge of the stellar disk during transit. A grazing transit produces a shallower, longer duration dip in brightness compared to a central transit. It's easier to miss and harder to confirm. but it still provides valuable information about the planet's size and potentially its atmosphere if observed with sufficient precision. The albedo of Proxima b, how much light it reflects, remains completely unknown but would tell us about its surface and atmosphere. A planet covered in clouds would have a high albedo, reflecting much of the starlight back into space. A dark rocky surface or an ocean would have a low albedo, absorbing most of the incoming light. Earth's average albedo is about 0.3, meaning 30% of sunlight is reflected. Venus, shrouded in thick clouds, has an albedo near 0.75. Mars, with its thin atmosphere and rusty surface, has an albedo around 0.25. Measuring Proxima b's albedo would require observing the planet directly and comparing reflected light to the star's output, a challenging observation even for next-generation telescopes. Atmospheric escape rates determine how quickly a planet loses its atmosphere to space. Several mechanisms drive escape. Thermal escape occurs when atmospheric molecules gain enough thermal energy to exceed the planet's escape velocity and fly off into space. This is most effective for light molecules like hydrogen and helium, which is why terrestrial planets retain heavier gases like nitrogen and oxygen while losing their primordial hydrogen envelopes. Non-thermal escape mechanisms include sputtering by stellar wind particles and photochemical escape driven by UV radiation breaking apart molecules. For Proxima b, with its intense stellar wind and UV radiation, non-thermal escape likely dominates. Quantifying these loss rates requires knowing the atmospheric composition, temperature profile, and planetary magnetic field strength, none of which we currently know. Volcanic activity on Proxima b could replenish atmospheric gases lost to space. On Earth, volcanic outgassing has been crucial in maintaining our atmosphere over geological time. Volcanoes release water vapor, carbon dioxide, sulfur dioxide, and other gases from the interior. If Proxima b has active tectonics and volcanism driven by internal heat, it could sustain an atmosphere even in the face of high escape rates. The balance between outgassing and escape determines the long-term atmospheric evolution. A planet with vigorous volcanism might maintain a thick atmosphere despite losing gases to space. A geologically dead planet would gradually lose its atmosphere with no mechanism for replenishment. Tidal heating calculations for Proxima b depend on its internal structure and orbital eccentricity. Even with an eccentricity of 0.1, the varying gravitational force as the planet moves closer to and farther from its star flexes the planet's interior, generating heat through friction. Jupiter's moon Io is the most volcanically active body in the solar system precisely because of tidal heating from Jupiter's gravity. If Proxima b experiences similar tidal heating, it could have active volcanism, geysers, and a molten interior even if stellar heating alone wouldn't provide enough energy. This would make the planet more geologically active and potentially more habitable. The rotation state of Proxima b remains uncertain despite the assumption of tidal locking. While most models predict synchronous rotation, the planet showing one face to the star permanently, other rotation states are possible. A planet in a higher-order spin-orbit resonance might rotate 3 times for every 2 orbits, like Mercury does around the Sun. This would mean different parts of the planet experience daylight and darkness over the course of multiple orbits, reducing temperature extremes and potentially improving habitability. Confirming the rotation state requires direct observation, either through detecting variations in reflected light as different surface features rotate into view or through detailed atmospheric modeling. Atmospheric superrotation could transport heat more efficiently than simple circulation models suggest. Superrotation occurs when the atmosphere rotates faster than the planet's surface, creating strong equatorial jets like those seen on Venus and Saturn's moon Titan. For a tidally locked planet, superrotation could move heat from the day side to the night side far more effectively than regular winds, potentially creating a more uniform temperature distribution. Detailed climate models incorporating superrotation show that tidally locked planets might be more habitable than initially thought, with larger regions maintaining temperatures suitable for liquid water. The magnetopause distance, where a planetary magnetic field balances the stellar wind pressure, determines how well a magnetic field protects the atmosphere. Earth's magnetopause sits at about 10 Earth radii on the sunward side, creating a protective bubble called the magnetosphere that deflects most of the solar wind around the planet. For Proxima b, the intense stellar wind would compress any magnetosphere significantly. If the planet has a magnetic field similar to Earth's, the magnetopause might extend only 2 or 3 planetary radii, providing less protection. A stronger magnetic field would push the magnetopause farther out, improving atmospheric retention. A weaker or absent magnetic field would allow the stellar wind to directly interact with the upper atmosphere, stripping it away. Auroral activity on Proxima b could be spectacular. Auroras occur when charged particles from stellar wind are funneled by magnetic field lines into the polar regions, where they collide with atmospheric molecules and cause them to emit light. On Earth, auroras appear as shimmering curtains of green, red, and purple light near the poles. On Proxima b, the combination of intense stellar wind and strong magnetic field, if present, could create near-permanent auroral displays far brighter than Earth's. Under the red light of Proxima, these auroras might glow in unusual colors, creating a constantly shifting light show visible across much of the night side. Atmospheric chemistry under red dwarf illumination differs fundamentally from chemistry under sun-like stars. The photochemistry, chemical reactions driven by light, depends on which wavelengths are available. Proxima emits relatively little blue and ultraviolet light compared to the Sun, but more red and infrared. This changes which chemical bonds can be broken by photons and which reactions proceed efficiently. Ozone formation, crucial for Earth's protective ozone layer, requires UV light. Under Proxima's spectrum, ozone formation might be suppressed, leaving the surface exposed to any UV that does reach the planet. Conversely, other photochemical pathways absent or minor on Earth might dominate on Proxima b, creating atmospheric chemistry unlike anything in our solar system. The possibility of subsurface oceans insulated from surface conditions offers another habitability pathway. Europa and Enceladus maintain liquid water oceans beneath ice shells kilometers thick, heated by tidal forces and insulated from the harsh space environment above. If Proxima b has a thick ice shell on its night side with liquid water beneath, life could exist in that ocean regardless of surface conditions. Such life would be isolated from direct stellar radiation, protected from flares, and potentially sustained by chemical energy from hydrothermal vents rather than photosynthesis. Finding such life would require different detection strategies, perhaps looking for gases released through cracks in the ice or detecting the ocean itself through radio wave transparency measurements. Impact cratering rates in the Proxima system depend on the population of asteroids and comets. In our solar system, Jupiter acts as both a shield and a threat. Its gravity deflects some impactors away from the inner planets, but also scatters others inward. The Alpha Centauri system lacks a Jupiter analog, as far as we know, which could mean different impact dynamics. More impacts could be bad for life, causing mass extinctions and sterilizing surfaces. Fewer impacts might mean less delivery of water and organic materials during planetary formation. The impact rate also depends on how the planetary system cleared out leftover debris during its formation and early evolution. Dust disks around Proxima might exist beyond the known planets. Many stars, including the Sun, have dust disks, collections of small particles from asteroid collisions and comet evaporation. Our solar system's zodiacal dust creates the faint zodiacal light visible from dark sites. If Proxima has a dust disk, observing it could reveal information about the outer regions of the system, potentially indicating where asteroid belts or Kuiper belt analogs exist. These regions are interesting because they're potential sources of water and organic material that could be delivered to inner planets through impacts. Orbital migration during the early history of the system could have reshuffled planetary positions. Planets don't necessarily stay where they form. Interactions with the protoplanetary disk of gas and dust, gravitational interactions between planets, and encounters with planetesimals can cause planets to migrate inward or outward. Hot Jupiters, gas giants orbiting very close to their stars, are thought to have formed farther out and migrated inward. If Proxima b formed beyond the ice line and migrated inward, it would have started with substantial water ice that partially evaporated as it approached the star. If it formed in place, its initial composition would have been drier, dominated by rocky silicates and metals. The protoplanetary disk around young Proxima would have been shaped by photoevaporation from the stellar radiation and winds. Disks don't last forever. They dissipate over a few million years as material accretes onto the star, forms planets, or is blown away. The timeline of disk dispersal affects planet formation. If the disk dissipated quickly, planets had less time to grow, potentially resulting in smaller planets. If it persisted longer, planets could accrete more material. Observations of young red dwarfs with disks, there are several within a few hundred light years, help us understand what Proxima's disk might have looked like and how Proxima B formed. The heavy element enrichment in Proxima's photosphere provides clues about planet formation. When planets form, they lock up heavy elements, metals in astronomical parlance, in solid bodies. If a star has planets, its photospheric abundances might show depletion of certain elements preferentially incorporated into planets. Alternatively, if the star accreted planetary material, say, a planet spiraled into the star and was consumed, its photosphere would show enrichment. Detailed chemical abundance measurements comparing Proxima to Alpha Centauri A and B, which formed from the same cloud and should have similar initial compositions, could reveal whether Proxima has consumed planets or experienced unusual chemical evolution. Lithium abundance in Proxima offers another diagnostic. Lithium is destroyed in stellar interiors at relatively low temperatures. Sun-like stars deplete their surface lithium as they age because convection carries it into regions hot enough to destroy it. Red dwarfs, being fully convective, should deplete lithium even more thoroughly. Measuring Proxima's lithium abundance and comparing it to predictions from stellar evolution models can test our understanding of mixing and nuclear burning in red dwarf interiors. Any discrepancies might indicate unusual internal structure or mixing processes. Stellar oscillations, pulsations of the star's surface driven by internal sound waves, offer a window into stellar interiors through asteroseismology. The Sun oscillates in millions of modes, creating patterns that reveal information about its internal structure, much like seismology on Earth reveals our planet's internal layers. Detecting oscillations in red dwarfs is harder because they're fainter and their oscillations have different characteristics, but it's possible. If we could detect and characterize oscillations in Proxima, we'd gain unprecedented insight into its internal structure, age, and evolutionary state. The X-ray luminosity of Proxima is surprisingly high for a red dwarf. X-rays are generated in the hot corona above the stellar surface, driven by magnetic activity. Proxima's X-ray output is about 1/1000th of its total luminosity, far higher than the Sun's ratio. This intense X-ray emission impacts any planetary atmosphere, driving ionization and heating the upper atmosphere, potentially enhancing escape rates. Over billions of years, X-ray and extreme UV radiation could have stripped away significant amounts of atmospheric mass from Proxima b, especially during the star's younger, more active phase. Young stars are more active than old stars. When stars first arrive on the main sequence and begin fusing hydrogen, they rotate rapidly and have strong magnetic fields, resulting in frequent flares and high-energy emission. As they age, they lose angular momentum through stellar winds, spin down, and become less active. Proxima is old, yet still quite active, suggesting that either it retained more angular momentum than expected or that red dwarfs remain active longer than Sun-like stars. If Proxima was even more active when young, the early environment for planet formation and any emerging life would have been extraordinarily harsh. The impact of stellar evolution on habitability over tens of billions of years raises interesting questions. Red dwarfs brighten very slowly as they age, unlike Sun-like stars that become significantly brighter over billions of years. This means Proxima's habitable zone has remained relatively stable throughout its lifetime and will continue to do so for trillions of years. A planet in the habitable zone today will remain there essentially forever, barring orbital migration. This long-term stability is an advantage for life. Once established, it has immense stretches of time to evolve without the star brightening and forcing migrations to new orbits. Comparative planetology between Proxima b and solar system bodies informs our expectations. Venus is similar in size to Earth but underwent a runaway greenhouse effect, creating surface temperatures hot enough to melt lead. Mars is smaller and lost most of its atmosphere, leaving a cold, dry desert. Earth sits between them, maintaining liquid water for billions of years. Where does Proxima b fall on this spectrum? Is it a Venus analog, Earth analog, or Mars analog? Its mass suggests Earth-like, but mass alone doesn't determine fate. Atmospheric composition, magnetic field, and stellar environment all play crucial roles. The concept of the Venus zone recognizes that planets can be too close to their star and undergo runaway greenhouse effects even if they start with water. The inner edge of the habitable zone is sometimes defined as the point where a runaway greenhouse becomes likely. For Proxima, with its lower luminosity, that inner edge is much closer to the star than Earth's distance from the Sun. But the intense UV and stellar activity might shift the habitable zone boundaries. Some researchers argue that red dwarf habitable zones should be narrower than traditional calculations suggest, making Proxima b potentially too close for stability. Atmospheric collapse on the night side is a risk for tidally locked planets. If temperatures on the night side drop below the freezing or condensation point of major atmospheric constituents, those gases will freeze out onto the surface. For a carbon dioxide atmosphere, this happens around 150 Kelvin. For nitrogen, around 63 Kelvin. If the entire atmosphere collapses onto the night side, the planet becomes airless, and any liquid water freezes. Only sufficient atmospheric mass and heat transport prevent collapse. Climate models show that atmospheres thicker than about 1 bar of pressure with efficient heat transport can avoid collapse. Thinner atmospheres are at risk. The day-night temperature differential drives powerful winds in tidally locked atmospheres. Air heated on the day side expands and rises, flows toward the night side at high altitude, cools and sinks, then returns to the day side at low altitude, a single enormous convection cell wrapping around the planet. These winds could reach hundreds of kilometers per hour, creating perpetual storms in the twilight zone where day and night meet. For any life on the surface, adapting to these constant gales would be essential. Perhaps life clings to sheltered regions, valleys, caves, or underwater, where winds are moderated. Seasonal variations on Proxima b, if the orbit is eccentric, would be brief but potentially significant. With an 11-day orbital period, a season, driven by orbital eccentricity, would last just a few days. The planet would spend a few days at periastron, closest approach to the star, receiving maximum stellar heating, then several days at apostron, farthest point, receiving minimum heating. For a planet with a thick atmosphere that responds slowly to changing stellar input, these variations might average out. For a planet with a thin atmosphere, temperature swings could be dramatic and rapid. The infrared emission from Proxima b would peak at wavelengths determined by its temperature. For a planet with an average temperature around 200 to 300 Kelvin, the peak emission falls in the mid-infrared, around 10 microns wavelength. This is convenient because Earth's atmosphere has a window in the mid-infrared where light passes through relatively easily, allowing ground-based telescopes to observe. Space-based infrared telescopes like JWST also operate efficiently at these wavelengths. Detecting Proxima b's thermal emission would allow us to measure its temperature directly and potentially distinguish the hot day side from the cool night side if we achieve sufficient angular resolution. Phase curve observations track how a planet's brightness changes over its orbit. As different hemispheres face Earth, the amount of reflected and emitted light varies. A planet with a hot day side and cool night side would show maximum brightness when the day side faces us and minimum brightness when the night side faces us. The shape of this phase curve reveals information about atmospheric heat transport. If the phase curve is nearly flat, heat transport is efficient. If it shows large variations, heat transport is poor. Several hot Jupiters have been studied this way. Applying the technique to Proxima b requires extreme precision because the signals are tiny, but it's theoretically possible. Obliquity, the tilt of a planet's rotation axis relative to its orbital plane, affects climate on Earth, giving us seasons as different hemispheres receive more direct sunlight at different times of year. For a tidally locked planet, obliquity has different implications. If Proxima b has significant obliquity, the substellar point, the spot where the star appears directly overhead, would vary over the course of a year. Except Proxima b's year is just 11 days, so any obliquity-driven variations would be rapid. Moreover, tidal forces likely damped any initial obliquity to near zero over millions of years, leaving the planet with its rotation axis perpendicular to its orbital plane. Resonances between rotational and orbital periods create interesting possibilities. Mercury is in a 3-to-2 spin-orbit resonance, rotating 3 times for every 2 orbits. This resonance arose because Mercury's orbit is eccentric, and tidal forces pushed it into the resonance rather than into synchronous rotation. If Proxima b's orbit is sufficiently eccentric, it too might avoid synchronous rotation and settle into a higher-order resonance. A 3-to-2 resonance would mean the planet rotates fully every 16.8 days, with the same hemisphere facing the star every other orbit. This creates a complex pattern of day and night cycles that would drastically affect climate and habitability. Planetary rings are possible around Proxima b, though there's no evidence for them. Rings form when material orbits too close to a planet to coalesce into a moon, within the Roche limit where tidal forces tear bodies apart. Saturn's rings are ice particles reflecting sunlight brilliantly. If Proxima b has rings, they'd reflect the star's red light, potentially making the planet more detectable through direct imaging. Rings could also cast shadows on the planet's surface, creating banded patterns of light and dark that might affect climate in unusual ways. Trojan objects, asteroids that share a planet's orbit, sitting 60 degrees ahead or behind in gravitationally stable Lagrange points, exist around several planets in our solar system. Jupiter has thousands of Trojans. Earth has at least one. Proxima b might have Trojans too, though detecting them would be extraordinarily difficult given the distances involved. Trojans could be interesting targets for future missions, potentially easier to reach than the planet itself while still offering insights into the system's composition and history. The question of whether Proxima b's star will enter a red giant phase is straightforward. It won't. Red dwarfs are too small to ever become red giants. Sun-like stars expand into red giants when they exhaust hydrogen in their cores and begin fusing helium. The outer layers expand enormously, potentially engulfing inner planets. Red dwarfs never reach this stage. When they exhaust their hydrogen, trillions of years from now, they'll simply fade gradually, becoming blue dwarfs and eventually white dwarfs. This means Proxima b's star will never threaten to consume the planet, providing ultimate long-term stability for any life that emerges. Habitability timelines for Proxima b stretch from its formation billions of years ago into the almost incomprehensibly distant future. If life emerged on the planet early, it has had up to 5 billion years to evolve, and could have tens of trillions of years more. Complex life on Earth took billions of years to arise, but once established, it diversified into an incredible array of forms. Given enough time, the same could happen on Proxima b. Intelligence might arise, civilizations might develop, and all while Proxima continues burning steadily, outlasting the Sun by factors of millions. The chemical composition of Proxima b's potential atmosphere would be shaped by its formation location and subsequent evolution. If the planet accreted in a region where temperatures allowed water ice to condense, it would have incorporated substantial volatiles during formation. These volatiles, water, carbon dioxide, nitrogen, methane, would have been released as the planet heated internally through radioactive decay and differentiation. The initial atmospheric composition depends on which gases were trapped during accretion and which were delivered later by comets. A planet forming closer to the star would have started drier, with an atmosphere dominated by volcanic outgassing of carbon dioxide, sulfur dioxide, and nitrogen from rocky minerals. Serpentinization reactions in Proxima b's subsurface could provide chemical energy for life independent of photosynthesis. Serpentinization occurs when water interacts with iron-rich minerals like olivine, producing hydrogen gas and heat. On Earth, hydrothermal vents driven by serpentinization support thriving ecosystems in absolute darkness at the ocean floor. Chemosynthetic bacteria use the hydrogen to fix carbon from dissolved carbon dioxide, forming the base of a food chain. If Proxima b has subsurface water in contact with appropriate minerals, serpentinization could sustain an entire biosphere regardless of surface conditions or stellar radiation. The nitrogen cycle on a potentially habitable Proxima b would differ from Earth's due to the radiation environment. Nitrogen is essential for life as we know it, forming the backbone of amino acids and nucleic acids. On Earth, lightning and certain bacteria fix atmospheric nitrogen into forms usable by other organisms. On Proxima b, intense UV radiation and stellar energetic particles could drive atmospheric nitrogen fixation through non-biological processes. Nitrogen oxides produced by radiation would dissolve in water, creating nitrates that organisms could potentially use. However, these same processes could also strip nitrogen from the atmosphere over geological time if not replenished by volcanic outgassing. Carbon isotope ratios in Proxima's spectrum reveal details about nucleosynthesis in previous stellar generations. Carbon-12 and carbon-13 are produced in different ratios by different stellar processes. The ratio observed in Proxima tells us about the history of star formation in this region of the galaxy. These measurements connect Proxima to the broader galactic chemical evolution, showing how generations of stars have processed material from the Big Bang's primordial hydrogen and helium into the diverse elements we observe today. Convective overturn timescales in Proxima's interior determine how quickly material cycles from core to surface. In a fully convective star, material rising from the fusion zone reaches the photosphere in a matter of months or years, not the millions of years required for radiative transport in the Sun's interior. This rapid mixing has profound implications. Freshly fused helium reaches the surface quickly. Any lithium in the star gets cycled down to temperatures where it's destroyed. The entire star maintains a remarkably uniform composition from center to surface, unlike the Sun's layered structure with different composition in different zones. Differential rotation, where different latitudes of a star rotate at different speeds, might occur in Proxima's convective envelope. The Sun's equator rotates faster than its poles, creating shear that helps drive the solar dynamo. Detecting differential rotation in Proxima would require tracking star spots at different latitudes over many rotation periods, measuring their individual rotation rates. Such measurements could revolutionize our understanding of dynamos in fully convective stars and explain why Proxima generates such a powerful magnetic field despite lacking the radiative convective boundary that drives the Sun's dynamo. Meridional circulation, large-scale flow patterns from equator to poles and back, might redistribute heat and magnetic flux in Proxima's interior. These flows, analogous to Earth's atmospheric circulation cells, could operate on timescales of decades or centuries, slowly transporting material and energy throughout the star. Observing signatures of meridional circulation would require long-term monitoring of star spots and activity patterns, searching for systematic drifts in active regions toward or away from the poles. The neutrino flux from Proxima is vastly lower than from the Sun due to the lower fusion rate. Neutrinos are nearly massless particles produced in nuclear fusion reactions. The Sun produces enormous numbers of neutrinos, about 65 billion pass through every square centimeter of Earth every second. Detecting solar neutrinos required massive underground detectors and decades of effort. Proxima, with its lower luminosity and slower fusion rate, produces proportionally fewer neutrinos. Detecting them would be impossible with current technology but would directly confirm nuclear fusion in the core and test stellar models. Mass loss through stellar winds gradually reduces Proxima's mass over time, though the effect is minuscule. Even with a wind 10 times stronger than the solar wind, Proxima loses only about 1 part in 10 trillion of its mass every year. Over billions of years, this accumulates to a negligible fraction of the star's mass. The wind's importance lies not in mass loss from the star but in its interaction with planetary atmospheres, where it can strip away substantial amounts of gas over geological time. The mixing length theory describes how convection transports energy through stellar interiors. In a convective zone, hot plasma rises in columns or cells called convective elements. These elements travel a characteristic distance, the mixing length, before dissolving into the surrounding plasma and depositing their heat. The mixing length parameter affects stellar structure models, changing predicted radii, temperatures, and luminosities. Calibrating this parameter for red dwarfs like Proxima requires comparing theoretical models with observational constraints like the measured radius and effective temperature. Magnetic reconnection events in Proxima's atmosphere release stored magnetic energy explosively, producing flares. Magnetic field lines become twisted and stressed by the star's rotation and convective motion. When oppositely directed field lines approach each other, they can reconnect, converting magnetic energy into kinetic energy, heat, and radiation. This process accelerates particles to high energies and heats plasma to millions of degrees, producing the X-ray emission observed during flares. Understanding magnetic reconnection in Proxima helps explain not just stellar flares but also solar flares and even flares in laboratory fusion plasmas. Coronal mass ejections from Proxima would be devastating for any planetary atmosphere. The Sun occasionally ejects billions of tons of plasma from its corona in eruptions called CMEs. When a CME impacts Earth, it can cause geomagnetic storms, auroras, and damage to satellites. Proxima likely produces CMEs as well, potentially more frequent and energetic due to its high activity level. A CME striking Proxima b would compress the planet's magnetosphere if it has one, or directly impact the atmosphere if it doesn't, stripping away atmospheric material and subjecting the surface to intense particle radiation. Photometric variability of Proxima caused by star spots creates challenges for detecting planetary transits. When a large star spot rotates across the visible hemisphere of the star, it reduces the overall brightness because spots are cooler and darker than the surrounding photosphere. This spot-induced variability can have similar amplitude and duration to planetary transits, creating false positives. Distinguishing transits from spots requires modeling the spot patterns, their sizes, temperatures, latitudes, and evolution, and subtracting their contribution to isolate any genuine planetary transit signal. Acoustic oscillations in Proxima's atmosphere could be detected through precise Doppler measurements. Sound waves propagate through stellar atmospheres, causing tiny velocity shifts as material moves up and down. These oscillations have characteristic frequencies determined by the star's internal structure. Detecting them requires measuring radial velocities with precisions of a few meters per second and searching for periodic signals in the frequency domain. Success would open up astroseismology of red dwarfs, providing constraints on interior structure currently impossible to obtain any other way. The chromosphere of Proxima, the region above the photosphere where temperature increases with altitude, is more prominent than in Sun-like stars. Spectral lines formed in the chromosphere show emission rather than absorption, indicating the gas is hot and glowing. The heating mechanism remains debated. Magnetic waves propagating from below might deposit energy in the chromosphere, or magnetic reconnection events might heat it directly. Understanding chromospheric heating in red dwarfs connects to understanding atmospheric heating in Sun-like stars, one of the outstanding problems in solar physics. Elemental abundances in Proxima's spectrum beyond just metallicity reveal nucleosynthetic histories. Elements like carbon, nitrogen, and oxygen are produced in different ratios by different types of stars. Massive stars produce more oxygen relative to carbon. Intermediate mass stars produce carbon-rich material. Measuring individual elemental abundances in Proxima and comparing them to theoretical predictions tests our understanding of galactic chemical evolution and the sources of different elements. The alpha element enhancement or depletion in Proxima indicates the timescale of star formation in its birth environment. Alpha elements like oxygen, magnesium, and silicon are produced primarily in core-collapsed supernovae from massive stars that evolve quickly. Iron comes largely from type I supernovae, which take longer to occur. A star rich in alpha elements relative to iron formed early when only massive stars had exploded. Normal alpha to iron ratios indicate formation after type I supernovae began contributing. Proxima's abundance pattern places it in the context of galactic history. Flare prediction for Proxima would be valuable for planning observations of its planets and assessing habitability. Some stellar flares show precursor signals, changes in magnetic field configuration, brightening in certain wavelengths, or characteristic oscillations. If Proxima's flares are predictable hours or days in advance, Observations could be timed to avoid them or specifically target them. Understanding flare triggers also informs models of how magnetic energy builds up and gets released, applicable to the Sun and other stars. The white light flares from Proxima, flares bright enough to be seen in visible wavelengths, not just X-rays or UV, indicate enormous energy release. Most stellar flares are detected in high-energy wavelengths produced by hot plasma and energetic particles. Seeing a flare in white light means the energy release is so intense that even the relatively cool photosphere brightens noticeably. These are the most powerful flares, releasing energies equivalent to billions of nuclear bombs within seconds to minutes. Starquakes, sudden rearrangements of a star's magnetic field or interior structure, might occur in Proxima. Analogous to earthquakes, starquakes release stored energy suddenly, potentially causing observable changes in luminosity, rotation rate, or magnetic field strength. Neutron stars exhibit starquakes when their crusts fracture, producing glitches in their rotation. Whether main sequence stars like Proxima experience analogous events remains speculative, but detecting one would provide unique insights into stellar structure. The stellar rotation axis orientation relative to the planetary orbital plane affects star-planet magnetic interactions. If the star's rotation axis is tilted relative to the planet's orbital plane, the stellar magnetic field structure experienced by the planets changes over the stellar rotation period. This could modulate how much stellar wind and magnetic energy the planets encounter. Measuring the stellar rotation axis orientation requires observing how star spots transit across the stellar disk or detecting rotational broadening in spectral lines at different position angles. Flux ropes in Proxima's magnetosphere, twisted bundles of magnetic field lines, could transport energy and material through the stellar atmosphere. The Sun ejects flux ropes during coronal mass ejections. These structures maintain their identity as they propagate through space, potentially crossing millions of kilometers before dissipating. If Proxima produces flux ropes, they could strike planetary atmospheres like whips, depositing energy and momentum in localized regions and creating transient auroral displays or atmospheric heating. The question of whether Proxima has a stellar corona, an extended atmosphere heated to millions of degrees, is answered affirmatively by X-ray observations. X-rays can only be produced by plasma at temperatures exceeding 1 million Kelvin, far hotter than the photosphere. Detecting X-rays confirms the existence of a corona. The heating mechanism generating such extreme temperatures in the low-density corona while the denser photosphere remains relatively cool is one of astrophysics' enduring mysteries, unsolved even for the Sun. Solar-stellar connection research uses Proxima and other stars as laboratories for understanding the Sun. The Sun is just one star, observed from one distance at one point in its evolution. Studying many stars of different masses, ages, and activity levels reveals general principles of stellar magnetism and activity. Proxima's extreme activity provides a window into what young, active Sun-like stars might have been like, informing our understanding of the Sun's history and the early solar system's radiation environment. The star spot coverage fraction on Proxima, what percentage of the surface is covered by spots at any given time, can reach 50% or more during high activity periods. In comparison, the Sun at solar maximum has spot coverage of less than 1%. Such extensive spot coverage dramatically reduces Proxima's luminosity during active periods and changes its spectrum because spots are cooler and emit more in red and infrared wavelengths while emitting less in blue and UV. Zeeman Doppler imaging combines spectroscopy and polarimetry to map magnetic field structures across a star's surface. Magnetic fields split spectral lines through the Zeeman effect, and the polarization of the split components reveals field direction and strength. By observing a star over multiple rotations and reconstructing which parts of the surface contribute to the spectrum at different times, astronomers can create two-dimensional maps showing magnetic field strength and polarity across the entire stellar surface. Such maps of Proxima would reveal the large-scale magnetic field structure and how it evolves over time. The Parker instability in Proxima's magnetic field could drive mass loss. Named after Eugene Parker, who predicted the solar wind, this magnetohydrodynamic instability causes magnetic flux tubes to rise buoyantly through the stellar atmosphere, dragging plasma with them. If the flux tubes escape the star's gravitational pull, they carry mass away in a magnetically driven wind. This mechanism might contribute to the enhanced mass loss rates inferred for active red dwarfs. Alphane waves, oscillations in magnetic field lines that propagate along them, could carry energy from Proxima's interior to its corona. These waves, predicted by Hannes Alphane, who received a Nobel Prize for magnetohydrodynamics research, travel at the Alphane velocity determined by magnetic field strength and plasma density. In the Sun, Alphane waves are thought to heat the corona and accelerate the solar wind. Similar waves in Proxima might explain its coronal heating and enhance stellar wind. The stellar dynamo cycle in Proxima, analogous to the Sun's 11-year sunspot cycle, remains uncertain. Some red dwarfs show long-term activity cycles revealed by decades of monitoring. Others appear irregular with no clear cycle. Proxima has been observed intensively for only a few decades, insufficient to detect a cycle that might span many decades or centuries. Continued monitoring might eventually reveal cyclic behavior in flare rates, star spot coverage, or chromospheric emission, indicating periodic reversals or reorganizations of the global magnetic field. Prominence eruptions on Proxima would be magnificent if we could observe them directly. Prominences are huge loops or sheets of plasma suspended above the stellar surface by magnetic fields. When they become unstable and erupt, they can fling billions of tons of plasma into space at speeds of hundreds of kilometers per second. Solar prominences observed in hydrogen alpha light appear as bright arcs extending hundreds of thousands of kilometers above the Sun's surface. Proxima's prominences would scale with the star's size, potentially extending several stellar radii into space. The convection zone depth in Proxima encompasses the entire star, from the fusion core to the photosphere. This differs fundamentally from the Sun, where the convection zone occupies only the outer 30% by radius. The boundary between radiative and convective zones in the Sun is sharp, marked by sudden changes in temperature gradient and composition gradients. Proxima lacks such a boundary, having a single convective zone with properties that vary smoothly from center to surface. Granulation patterns on Proxima's surface, the cellular patterns caused by convection cells bringing hot plasma up and cool plasma down, would be tiny if we could resolve them. Solar granules are about 1,000 kilometers across, covering the Sun's surface in a constantly shifting pattern like boiling water. Proxima's granules would scale with the smaller pressure scale height in the star's denser atmosphere, perhaps only a few hundred kilometers across. Future interferometric observations combining light from multiple telescopes might achieve sufficient angular resolution to image Proxima's surface and see its granulation directly. The limb darkening profile, how a star's brightness decreases from center to edge when viewed as a disk, depends on atmospheric structure. At the center of the stellar disk, we see deeper into the atmosphere to hotter layers. Toward the edge, we see only the upper, cooler layers, so the star appears dimmer. Measuring limb darkening tests, atmospheric models. Proxima's limb darkening can be measured during transits if any planets do transit, as the planet occults different parts of the stellar disk during ingress and egress, probing the brightness variation. Convective overshoot, where convective elements penetrate into the layers above or below the convective zone, might affect Proxima's structure. In the Sun, convective overshoot at the base of the convection zone mixes material from the radiative zone into the convection zone. For Proxima, convective overshoot at the surface could affect the photospheric temperature structure and atmospheric dynamics, changing the spectrum slightly. Modeling overshoot requires sophisticated three-dimensional hydrodynamic simulations. The transition region between Proxima's chromosphere and corona, where temperature jumps from 10,000 Kelvin to 1 million Kelvin over just a few hundred kilometers, is a site of intense physical processes. Understanding this transition remains challenging. The rapid temperature increase requires enormous energy input, yet the plasma density drops rapidly with altitude, making efficient energy transport difficult. Observations in UV wavelengths sample this transition region, revealing clues about heating mechanisms. The mass-luminosity relation for red dwarfs is steep, meaning small changes in mass produce large changes in luminosity. A star with half the Sun's mass has only 3% of the Sun's luminosity. Proxima, at 12% solar mass, has only 0.17% solar luminosity. This steep relation means that small uncertainties in mass measurements translate to significant uncertainties in predicted luminosity, making precise tests of stellar models challenging. Magnetic buoyancy drives the emergence of magnetic flux from Proxima's interior to its surface. Magnetic field lines are buoyant because magnetic pressure inside flux tubes is higher than gas pressure outside, making the tubes less dense. They rise through the convection zone, eventually breaking through the photosphere and creating star spots, prominences, and other active region phenomena. The rate of flux emergence depends on the strength of the internal dynamo and the efficiency of buoyant rise, which in turn depends on the convection zone structure. The dynamo number, a dimensionless parameter characterizing dynamo efficiency, combines rotation rate, convection zone depth, and other properties into a single figure of merit. Stars with similar dynamo numbers should have similar magnetic activity levels despite different masses or ages. Calculating Proxima's dynamo number and comparing it to other stars tests our understanding of stellar dynamos and predicts which stars should be magnetically active. Magnetic helicity, a measure of how twisted and linked magnetic field lines are, might build up in Proxima's magnetic field over time. Helicity is approximately conserved in ideal magnetohydrodynamics, meaning once created, it can only be destroyed slowly by resistive dissipation or ejected from the star in CMEs. Excessive helicity buildup might trigger eruptions as the magnetic field becomes too twisted to remain stable. Tracking helicity injection and ejection in stellar models helps explain activity cycles and eruption frequencies. The meridional flow velocity in Proxima's convection zone determines how quickly material circulates from equator to poles and from surface to core. In the Sun, meridional flows are a few tens of meters per second, taking years to decades to complete one's circulation. Detecting and measuring these flows in other stars is extraordinarily difficult, requiring helioseismic or astroseismic techniques that can probe internal dynamics. Success would constrain convection models and improve predictions of how quickly chemical anomalies mix throughout the star. The radiation pressure in Proxima's atmosphere exerts outward force on material, though far weaker than in luminous massive stars. In the most luminous stars, radiation pressure can exceed gravitational force, driving powerful stellar winds and even affecting stellar structure. For Proxima, radiation pressure is negligible compared to gas pressure and gravity. However, radiation pressure does affect dust grains in the circumstellar environment, potentially clearing out small particles from regions close to the star and influencing planet formation processes in the protoplanetary disk. Opacity sources in Proxima's atmosphere determine how efficiently photons can escape. At the cool temperatures of red dwarf photospheres, bound-free absorption by negative hydrogen ions dominates opacity in the Sun's atmosphere, but in Proxima's cooler regions, molecular opacity becomes important. Water vapor, titanium oxide, and other molecules absorb light at specific wavelengths, creating the complex spectrum we observe. Understanding which molecules contribute to opacity at different depths and temperatures is essential for accurate atmospheric modeling. The equation of state-relating pressure, density, and temperature in Proxima's interior must account for partial ionization and degeneracy effects. At the high densities in the stellar core, electrons start to become degenerate. Quantum mechanical effects prevent them from being compressed arbitrarily, providing additional pressure support. This electron degeneracy pressure becomes increasingly important for the smallest red dwarfs approaching the hydrogen burning limit. For Proxima, degeneracy provides a modest contribution to pressure, affecting the central density and temperature required for fusion. Nuclear reaction rates in Proxima's core proceed through the proton-proton chain, the same fusion pathway that powers the Sun. The rate depends exponentially on temperature, which is why small differences in core temperature produce large differences in luminosity. At Proxima's core temperature of about 3 million Kelvin, fusion proceeds much more slowly than in the Sun's 15 million Kelvin core. The specific reaction rates for each step in the proton-proton chain have been measured in laboratory experiments and refined through theoretical calculations. Neutrino cooling in Proxima's core carries away a fraction of the energy generated by fusion. Every fusion reaction producing helium-4 from hydrogen releases energy partly as gamma rays that heat the surrounding plasma, and partly as neutrinos that escape the star without interaction. In the Sun, about 2% of fusion energy escapes as neutrinos. The fraction is similar for Proxima, but the absolute neutrino luminosity is far lower because of the reduced fusion rate. Convective energy transport efficiency determines the temperature gradient in Proxima's interior. If convection is highly efficient, carrying heat from core to surface rapidly, the interior can be nearly isothermal, constant temperature throughout. If convection is less efficient, temperature must increase toward the center to drive heat flow. The efficiency depends on the vigor of convective motions, which relates to the supradiabatic excess. How much the actual temperature gradient exceeds the adiabatic gradient that would exist in a perfectly convective medium. The pressure scale height in Proxima's atmosphere, the altitude over which pressure drops by a factor E, is much smaller than in the Sun due to stronger surface gravity relative to temperature. A smaller scale height means the atmosphere is compressed into a thinner layer, with density and pressure changing more rapidly with altitude. This affects atmospheric dynamics, spectral line formation, and the structure of the photosphere and chromosphere. Ionization fractions throughout Proxima's atmosphere vary from nearly complete ionization in the deep interior to mostly neutral atoms and molecules in the cool photosphere. Hydrogen transitions from fully ionized in the core to neutral atoms in the photosphere. Metals follow similar transitions at different depths depending on their ionization potentials. Computing accurate ionization fractions requires solving Saha equations that balance ionization and recombination rates, accounting for temperature, density, and radiation field at each depth. The virial theorem relates a star's total kinetic energy to its gravitational potential energy in hydrostatic equilibrium. For a star supported by gas pressure, the kinetic energy of thermal motions equals half the gravitational potential energy. This fundamental relation constrains stellar structure and explains why stars contract and heat when they lose energy. The virial theorem requires that losing energy increases kinetic energy, seeming paradoxical but thermodynamically necessary. The Kelvin-Helmholtz timescale estimates how long a star could shine by contracting gravitationally without nuclear fusion. It equals the gravitational potential energy divided by the luminosity. For the Sun, this timescale is about 30 million years, far shorter than the Sun's actual age, proving that gravitational contraction alone cannot power the Sun and necessitating nuclear fusion. For Proxima, the Kelvin-Helmholtz timescale is much longer due to lower luminosity, about 500 million years, but still far shorter than its actual age. The nuclear timescale, representing how long a star can burn its hydrogen fuel, equals the available fusion energy divided by the luminosity. For Proxima, with access to essentially all its hydrogen through convective mixing, this timescale is measured in trillions of years. This is the fundamental reason red dwarfs outlive other stars. Their combination of huge fuel supply and frugal consumption rate gives them extraordinary longevity. The dynamical timescale, representing how quickly a star responds to dynamically destabilizing forces, equals the sound crossing time from center to surface. For Proxima, sound takes about 3 hours to traverse the stellar interior. If something were to suddenly disturb hydrostatic equilibrium, the star would respond on this timescale, either contracting or expanding to restore balance. This is the shortest fundamental timescale in stellar structure, far shorter than thermal or nuclear timescales. Convective turnover time in Proxima's interior, how long a convective element takes to complete one circulation from deep interior to surface and back, is estimated at months to years based on mixing length theory. This timescale affects how quickly chemical composition anomalies are mixed throughout the star and influences magnetic field generation by determining how rapidly magnetic field lines are stretched and twisted by convective motions. The critical rotation period at which centrifugal force at the equator equals surface gravity is about 1 hour for Proxima. At rotation periods shorter than this, the star would be unstable and shed mass from its equator. Proxima's actual rotation period of 83 days is far longer, so centrifugal effects are negligible. However, newly formed red dwarfs rotate much faster, with periods of days or even hours, approaching the breakup limit and producing extreme magnetic activity. The moment of inertia of Proxima determines how its rotation responds to angular momentum changes. A fully convective star has a more centrally concentrated mass distribution compared to radiative stars, affecting the moment of inertia. When angular momentum is lost through stellar winds, charged particles escaping along magnetic field lines carry away angular momentum. The star must spin down. The timescale for rotational evolution depends on the moment of inertia and the efficiency of angular momentum loss. The gyrochronology age-rotation relation uses rotation period to estimate stellar ages, calibrated using star clusters of known age. Young stars rotate rapidly. As they age and lose angular momentum through magnetized winds, they spin down. The relationship between age and rotation period differs for stars of different masses. For red dwarfs, the relation is poorly calibrated because few red dwarf members of young clusters have measured rotation periods. Improving gyrochronology for M dwarfs would provide a valuable age dating technique. The magnetic activity rotation relation shows that faster rotating stars are more magnetically active, with more spots, stronger magnetic fields, and more frequent flares. This relation holds across stellar masses from red dwarfs to F-type stars. The physical explanation involves the dynamo mechanism. Faster rotation enhances magnetic field generation. Proxima's rotation period of 83 days places it in a regime where moderate activity is expected, though it appears somewhat more active than average for its rotation rate. Magnetic cycles in solar-type stars often correlate with rotation. Faster rotators have shorter cycles. If Proxima has a magnetic cycle, its 83-day rotation period might suggest a cycle period of decades, though this is highly uncertain. Some red dwarfs show no clear cycles at all, maintaining relatively constant activity levels for decades. The presence or absence of cycles might relate to whether the dynamo operates in a cyclic or chaotic regime, possibly depending on the ratio of rotation period to convective turnover time. The Rossby number, defined as rotation period divided by convective turnover time, is a key parameter characterizing dynamo efficiency. Stars with low Rossby numbers, fast rotation compared to convection timescale, have strong, organized magnetic fields. Stars with high Rossby numbers have weaker, more chaotic fields. Proxima's Rossby number is near unity, placing it in a transitional regime where the dynamo is active but not saturated. Activity saturation occurs when magnetic activity indicators like X-ray luminosity reach a maximum value independent of further increases in rotation rate. The fastest rotating stars have X-ray luminosity about 1,000th of their bolometric luminosity, and rotating even faster doesn't increase X-rays further. The saturation is thought to occur when the stellar surface becomes completely covered by active regions, so adding more magnetic flux simply replaces existing flux rather than increasing total activity. The age-activity rotation connection implies Proxima's moderate rotation period and activity level indicate an old age, consistent with its membership in the Alpha Centauri system. Young red dwarfs rotate in days and produce flares far more frequently and energetically than Proxima does now. Proxima has spun down over billions of years, reducing but not eliminating its activity. It will continue spinning down over the coming billions of years, eventually becoming a slowly rotating, magnetically quiet star. Stellar winds carry mass and angular momentum away from Proxima through a magnetized outflow. The wind is accelerated by thermal pressure in the hot corona and by magnetic forces that convert magnetic energy into kinetic energy. As the wind flows outward, it remains coupled to the stellar magnetic field out to several stellar radii. Beyond this point, the field lines are dragged by the wind and stretched radially. The resulting magnetic stress exerts a braking torque on the star, removing angular momentum and causing spin down. The Alfvén radius, where the wind speed equals the Alfvén speed and the wind decouples from the magnetic field, is several stellar radii from Proxima. Inside this radius, magnetic forces dominate and control the wind flow. Outside, the wind flows freely. The location of the Alfvén radius affects the efficiency of angular momentum loss. A larger Alfvén radius means magnetic forces act over a longer lever arm, removing more angular momentum per unit mass lost. The terminal velocity of Proxima's stellar wind, reached far from the star where acceleration ceases, is estimated at several hundred kilometers per second based on analogs to the solar wind and scaling with coronal temperature. Fast winds remove mass and angular momentum more efficiently than slow winds. The wind speed also affects its interaction with planetary atmospheres. A faster wind exerts more ram pressure and strips atmospheres more efficiently. The wind composition reflects the stellar photospheric composition plus modifications from processes in the corona. Elements with low first ionization potentials are preferentially enhanced in the solar wind relative to their photospheric abundances, a phenomenon called the FIP effect. Whether Proxima's wind shows a similar FIP effect remains unknown, but studying it would reveal coronal heating and wind acceleration processes. Charge exchange between stellar wind ions and neutral atoms in planetary exospheres produces X-ray emission detectable from Earth. When a highly charged ion like O7+ captures an electron from a neutral atom, the electron cascades down to lower energy levels, emitting X-rays. This process has been detected in comets interacting with the solar wind and might occur in the interaction between Proxima's wind and Proxima B's upper atmosphere if the planet has sufficient neutral hydrogen escaping to form an exosphere. Bow shocks form where the stellar wind encounters the local interstellar medium, creating a compressed, heated boundary layer. The Sun's bow shock, if it exists, is too far away to study in detail, beyond the heliopause at over 100 AU. Proxima's bow shock shape and location depend on its wind properties and the density and velocity of interstellar material it's moving through. High-resolution infrared observations might detect emission from dust or gas heated at the bow shock, revealing information about the wind strength. The astrosphere, the bubble carved out by stellar wind in the interstellar medium, around Proxima extends for hundreds of AU, analogous to the Sun's heliosphere. This region is filled with Proxima's wind plasma and magnetic field, shielding the planetary system from interstellar cosmic rays and neutral atoms. The size and shape of the astrosphere depend on the balance between wind pressure and interstellar pressure. If Proxima moves through a dense interstellar cloud, the astrosphere could be compressed to just a few tens of AU. Cosmic ray modulation by the astrosphere affects radiation levels in the planetary system. Galactic cosmic rays, high-energy particles from supernova remnants and other sources throughout the galaxy, attempt to penetrate into the planetary system but are partially deflected by the stellar wind's magnetic field. During periods of strong stellar wind, cosmic ray intensity decreases. During quiet periods, more cosmic rays reach the inner system. This modulation might affect atmospheric chemistry and radiation doses on planetary surfaces. Pickup ions form when neutral interstellar atoms penetrate into the astrosphere, become ionized by stellar UV radiation or charge exchange, and are then accelerated by the stellar wind's electric field. These ions gain significant energy and contribute to anomalous cosmic rays, a low-energy component of cosmic rays generated locally within astrospheres rather than in distant supernovas. Detecting pickup ions from Proxima would require in situ measurements impossible with current technology. The heliopause equivalent for Proxima, the boundary where stellar wind pressure equals interstellar medium pressure, lies somewhere between tens and hundreds of AU depending on wind strength and local interstellar density. This boundary separates the star's domain from interstellar space. Any interstellar mission to Proxima would cross this boundary, transitioning from the stellar environment to the true interstellar medium between stars. Dust grain dynamics in the Proxima system are shaped by radiation pressure, stellar wind drag, and gravity. Small dust grains feel radiation pressure strongly, potentially exceeding gravitational attraction and being blown out of the system. Larger grains remain bound but their orbits evolve under drag forces. The size distribution of dust, which grain sizes are present in what proportions, reflects the balance between production through asteroid collisions and removal through these dynamical processes. Poynting-Robertson drag causes dust grains to spiral inward toward Proxima over timescales of thousands to millions of years. When a grain absorbs sunlight, it heats up and re-radiates the energy thermally. Because the grain is orbiting, it re-radiates preferentially in its direction of motion, creating a small drag force that removes orbital energy. Eventually, grains spiral into the star and are vaporized. The timescale depends on grain size and orbital distance. Smaller grains and closer orbits spiral and faster. Dust collisions fragment grains, producing smaller fragments that are more susceptible to radiation pressure and drag. A collisional cascade grinds larger parent bodies down to dust, then grinds the dust to smaller fragments, eventually removing material from the system. The balance between collision rates, fragmentation properties, and removal mechanisms determines the steady-state dust disk properties. Resonant structures in dust disks can be created by planets. When dust grains orbit at locations where their orbital periods are simple ratios of a planet's period, gravitational perturbations accumulate coherently, creating overdense rings and gaps. Observing such resonant structures in Proxima's dust disk would reveal the presence of planets through their gravitational influence on dust dynamics, even if the planets themselves are too faint to detect directly. The zodiacal light equivalent around Proxima, sunlight scattered by dust grains creating a faint glow along the ecliptic plane, would be redder than our zodiacal light due to Proxima's redder spectrum. An observer on Proxima b might see this scattered light as a diffuse red glow brightening the night sky in the plane of the planetary system, similar to zodiacal light on Earth but shifted in color. Exozodiacal dust around nearby stars has been detected through infrared excess emission. The star appears brighter in infrared than expected from its temperature because warm dust emits additional infrared radiation. Searching for infrared excess around Proxima could reveal whether a significant dust disk exists. So far, no clear detection has been made, suggesting either the dust is minimal or too cold to produce detectable excess at the wavelengths observed. The ice line in Proxima's protoplanetary disk, the distance beyond which water ice is stable, was located very close to the star, perhaps just 1 to 2 AU away. Inside the ice line, temperatures were too high for water ice, so planets forming there accreted mainly rock and metal. Beyond the ice line, water ice dramatically increases the solid material available for planet building, potentially explaining why gas giants in our solar system formed beyond the ice line where more solid material was available to build large cores. Pebble accretion in Proxima's protoplanetary disk might have been the dominant planet formation mechanism. In this process, small particles, pebbles millimeters to centimeters in size, drift inward through the disk due to gas drag. When they encounter a growing planetary embryo, the embryo's gravity can capture them efficiently. Pebble accretion can build planets rapidly, potentially forming Proxima b in less than 1 million years, solving the problem of how to build planets before the gas disk disperses. Planetary migration through the gaseous protoplanetary disk might have moved Proxima b from its formation location to its current orbit. Disk-planet interactions create torques that transfer angular momentum between the disk and planet. Typically, these torques cause inward migration, Type 1 migration for small planets, Type 2 migration for larger planets that open gaps in the disk. If Proxima b formed farther out and migrated inward, it would have passed through different temperature zones, affecting its composition and volatile content. The disk dispersal timescale for Proxima's protoplanetary disk, determined by photoevaporation and accretion onto the star, was likely a few million years. Young stars blow away their disks through energetic radiation and winds. Once the disk disperses, planet formation largely ceases, and planets are left in their final orbits. The timing of disk dispersal relative to planet formation determines how large planets can grow, and whether gas giants can form. Oligarchic growth describes the intermediate stage of planet formation where several large planetary embryos dominate their feeding zones, accreting material while preventing other embryos from growing. Each oligarch controls a region of the disk, and they grow at similar rates until they've consumed most of the available material. Then the system transitions to giant impacts between oligarchs, the final stage that produces terrestrial planets of their final masses. The late veneer of volatiles delivered to Earth by comets and asteroids after the primary accretion might have occurred similarly on Proxima b. If the planet formed dry inside the ice line, subsequent impacts could have delivered water and organic materials. The timing and magnitude of late veneer delivery affect habitability. Too little water and the planet remains dry. Too much and it becomes a water world with no exposed continents. Isotopic fractionation in Proxima B's water, if it exists, would reveal the sources of that water. Different reservoirs in the protoplanetary disk, comets, asteroids, planetesimals, have characteristic isotopic ratios of hydrogen, deuterium to hydrogen ratio, oxygen, and other elements. Measuring these ratios in Proxima B's atmosphere or oceans would indicate whether its water came from local asteroid-like material or from comets formed in the outer disk and delivered inward.